So in the previous lectures we have learned how we can calculate dead loads and how we can calculate the live loads. So now in this lecture we shall learn that how we can take care of the staircase loadings that shall act on our structure. So this is basically the typical arrangement for this particular staircase. So what we can modification that we can do in this scenario is that we can delete the floor beam from this point to this point, as this area is a mid landing level only. So what we need to do here is that we can select this particular area on which we do need to apply the staircase loading, and then we can model the mid landing beams here. And side by side we can now delete the floor beams here. So after that there are two approaches here. The number one approach is that what some people do is that they model the whole slab here for the staircase. So that I never advise, not in the ETABs and nor in the STAT also. That for simple structures we don't need to model the staircase because it just adds to the complicacy. So what we can do in this case is that we can just calculate the equivalent UDL on the floor beams, so that the loading that shall be acting on the staircase are accounted for. So this is just a rough Excel file in which we can enter the dimensions here, and this is nothing but 4 meter by 4.3 meter span, and staircase will run along 4.3 meter span. So we can enter 4.3 and 4 here. Floor height we can enter the from that is as 3.5 meters here, this value, and after that we can enter the grade of concrete and steel, rise rated also, landing width also, and effective span also. So effective span shall be as per the standards only. So this is just a rough and approximation method, the thing that I am doing here. So now in the small d requirement, its effective that requirement is in the range of 135 mm. So taking the cover of 25 mm, we can take our capital D, that is total depth is 165 mm. And we can enter the live loading on the staircase. It is 4 as per the standards, and floor finish also we can take, let us say, 1.2 kN per meter square. So the area of steel that is requirement is coming in the range of 12 dia 160. So we can take it as 12 dia 120 mm. That is, we should always be on the conservative side only. And the data that needs to be input is in STAT is in the range of 18 kN per meter for the dead load, and 9.3 kN per meter for the in the form of UDL for the live loads. So we go to the STAT model here, and we can go to dead load. We can add member load here, and we can enter it as minus 18. It is in the range of 17.84. Conservative we can take it as 18 kN per meter, and we can assign the loadings here on the beams. If the things are not clear, you can go to the editor and switch off these contours for the floor loadings. So we can left click on assign to selected beams and yes, and after that we can also assign the live loadings. Live loading is in the range of 10 kN per meter, that is approximately 1 ton per meter. So on the same beams we do need to apply the live loading also. So we enter the member load here, minus 10 kN per meter, and again left click on assign to selected beams and yes. So now we have applied the dead loads. Now we have applied the live loads also. We have defined the ELX parameter also and ELZ parameter also. And after that we do need to do one important thing here. Here we can see that under the seismic definition there are no loadings assigned except for the self weight of the structure. So we can go to the editor file here, and here what we need to do is that we do need to select the dead loads here and live load values here. So we go to the self weight 1 option here. This is the syntax in which the seismic definition is defined. Here we can just copy paste As a token to remember, we can like enter the stars here. We do need to change the load as weight, and after that what we we need to do here is that we need to remove this minus sign and remove the GY here. We can remove the 02 here, otherwise it will not read the syntax. So this is just a syntax for the like member UDLs, and after that we do need to change flow load to weight here. We remove the minus sign here, GY here, and again we do need to remove the, or what we can do here is that we can just press Ctrl X option on the keyboard, remove this member load command and remove the GY and minus sign here. After that we can enter the flow weight here, and to remember we can enter live load here. If we are writing something after star, then it will be considered as comment. Or what we can do is that we can just select the words here and then left click on this option here. If we want to remove the comment, we can just left click on this option, and after that we do need to remove the sign again here. And for live loading we do need to take the up to there is the clause to reduce the live load as per for the seismic loadings, and as per the clause 5.4.3.1 of IS 1893-2016, we can reduce the imposed load in the calculation of seismic weight. So up to and including 3 we do need to take 25%, and above 3 we need to take 50% of that loading. So here in this case the loading is 3, so up to and including 3 it is 25%, so we need to enter 0.75 here, and this is 4, so we do need to take 50%, that is 2. So 2 2 into 0.25, it is 0.5, and we do not need to take the terrace live loading for the calculation of the seismic weight. And we can put this data in the below member weight only, remove the member load here, and then just enter the data here. So what basically we have done is that we can just close the editor file here. If we go to the seismic definition again, so here we can see that all the commands are now defined here. So basically there are two options or two ways with which we can put the or instruct the stat at what exactly is the seismic weight of the structure. One is the editor file method that we have just concluded. Other is that we can just left click here and left click on add here. So here we can see that the member weight, element weight, reference load of floor weights command is coming. So you can also just press on corridor section here, and then for corridor, as the loading was in the range of 4 kN per meter square, so we can enter 2 here. So there are this is somewhat a tedious method to do, and there are chances that you might miss some loading when we are going by this approach. So I always advise people to go with the editor file approach and just copy paste the data in the below the seismic weight definition, and then we can just design the structure. So in this lecture we have learned how we can define the loadings under the seismic definition and how we do need to take care of the loadings for the staircase. In this lecture we shall learn how we can define the response vector cases. Now before defining the response vector cases, some of you might be getting confused that when we have defined this ELX, ELY and ELZ cases, why we are defining the response vector cases. There are two methods with which we can design the structure. I have explained this in the previous lectures also. One is the static earthquake method, one is the dynamic earthquake method. And the problem with the dynamic earthquake method is that we do need to scale the forces that are coming from the dynamic to the static. So we cannot just define the response vector cases as 1, 2 and 3 and just define the structure. As per all the country design standards, For American, we do need to match up to 85%, and for India, we do need to match up to the 100% of whatever results we are getting here. So that is why I have first of all defined the ELX and ELZ, and after that we have defined the response vector cases. And the beauty of this software is that the software will automatically tell us that what exactly is the scale with which we do need to upscale the response spectra results to match with the static earthquake results. So like going back to this RSX and left click on add here we can get the response spectra option. So we can select the code as IS1893, combination method CQC we can select, subsoil class as medium soil, and as this is a X direction loading, so we can enter X, and the value that needs to be entered here is Z divided by 2R. So in our case the value of Z is 0.16 and R value is 5. So the value that we need to enter there is 0.16 divided by 10, that is 0.016. So we enter response spectra here, again repeating the procedure here, 0.016, and scale we can enter here is 1. Please note that subsoil class is very important thing that you do need to refer from the this is geotechnical soil report. Sometimes it do happens that the area on which you are designing your building is a soft soil, soil or a like marshy area in which the water table is very high. So in that case it may happen that your soil may be classified as soft soil. So you do need to like remember that always refer to the geotechnical report before you enter this data here, and left click on add here. Similarly, we do not need to define the response spectra Y case in our structure, as this is the building is in a low seismic zone. And again we repeat the same procedure here, subsoil class as medium soil, and direction we enter it as Z.016, and scale we enter it as 1. Left click on add here. So now we have defined the response spectra cases for the X direction as well as for the Z direction. Now we are almost finished with defining all the load cases here, and if we move on to the like understanding what exactly should be our further procedure as per the standards. So the code is guiding us that we do need to take the effect of earthquake along all the 3 directions when we do need to take account of the vertical earthquake shaking also. And as our structure is not satisfying any of these conditions here, so we do need to take the effect of only the 2 orthogonal directions here. Now what I can do to save my work is that I can just define these load cases and then just move on to the next lecture. But I want you to reduce your work for the for this type of structure also. So maybe it might happen that you do need to design a structure in seismic zone 4 or seismic zone 5. Then you cannot take these load combinations. So to reduce your work, I have attached a particular editor file for which is having the syntax that you can follow in each and every structure. The syntax for that editor file is that first of all we can define the ELX, ELZ and ELY. Then obviously we have already entered this perform analysis and change command, and then we can define dead load, live load, wind loads and response spectra load cases. Now we are finished up to this level. After that there is no harm in if this response spectra or this ELY load case is empty, and if by chance you are designing a structure in seismic zone 4 or 5, you can define the ELY and RSY cases also. After that there are 2 approaches here. One is that when we do need to define the load combinations, there are 2 methods here. We can left click on load cases details here, and we can go to define combinations and manually for example we want 1.5 dead load plus ELX, so we can left click here and then we can enter the 1.5, then we can enter 1.5 dead load plus live load. So if we if you are you are designing a structure for this type of combination, you can imagine how much number of load combinations you need to design in your structure. So that is a very tedious task, and if I shall do all this in front of you now, it will take more than 1 hour. So to make the things short, what I am doing here is that I am providing you with the typical syntax file that you can follow for any type of structure. In this syntax file, what I have done is that to entertain this ELX plus 0.3 ELY plus minus 0.3 ELZ, or this ELY plus minus 0.3 ELX plus minus 0.3 ELZ. So what I had done here is that I have just made a separate load combination for these things. So as we are doing the dynamic analysis, not static analysis, so that is why I have considered RSX, not ELX. But in the separate lecture, for example, if you want to do the static earthquake analysis, that we will do in the next lecture. So you don't need to worry about how we can do the static analysis. We will shall do the static analysis for an office building in the next section. But in this section, what we are doing here is that we are just learning how to do the dynamic analysis. And if we can do dynamic, then there is the static analysis is very easy. So coming back to this point, so I have defined from load combination 101 to 124. So I have defined all the three possibilities, and with the syntax, that is 10 times 1, 11 times 0.3 and 12 times 0.3. 10 times 1, 11 times 0.3 and 12 times minus 0.3. Similarly, these 24 load combinations are just to entertain this part here. And then it is just typical old thing that we do need to follow in the load combinations here. So these are the wind load combinations, and for after that, this is the part which shall take care of this complex load combination method here. So what we are doing here is an 1.5 times dead load plus response spectra or earthquake load cases. So 1.5 times dead load plus 101, and 101 is nothing but this whole thing here. So similarly, I have defined all these load combinations here, and this is the effect to account for the overturning here. And after that, I have also defined the service load combinations here. Now how we can reduce our work, I have defined, I've seen people working there, working very hard to define these load combinations, but there's no need to, if you can just simplify your work by making a standard or by making a standard editor file, then you should do that. So there's no need to waste your time. So we can just copy all this data here, and then we can go to the editor file of our structure here. We can move over to this soil type 2 here, and after load type 12, we can just copy this file here. After that, here we can enter the perform analysis also. So now we have defined all these load combinations here, and then close this window here. So here we can see that now we have reduced our work by just copy pasting the whole data here. So I've seen many new engineers, what they usually do is that they just left click on add here and then go to auto load combination, select load combination as Indian code, general structures, and then just generate loads here. But this thing shall not entertain this thing. So that is the weakness of this auto load combination option here. So this is also, what should I say, a rough approach to do the analysis. But if you are working professionally, then you do need to take care of all the latest earthquake standards and all the latest design standards. So coming already we have defined the analysis command here. So here we can see that perform analysis is now written here. So now we are done with defining the load cases and load combinations. After that, we have missed one very important part here, that we have not defined the mass source for the response spectra load cases here. So what we need to do here is that we do need to go to reference load definition here. Loading type we need to refer here as mass, and we can enter the title as mass source. So without this reference loading of mass, loading type mass here, the response spectra case shall not be running in the start. So we can just add a pseudo loading here. So let us say we enter self weight x as 1, y as 1 and z as 1, so that we can easily find this mass source option in the editor file. As of now, we shall shift on to the working in the editor file. So we can go to the editor file here, and we can go look for this self weight one, that is mass source option here. So we do need to define the mass source here. So we can enter self weight x1, self weight y1 and self weight z1. Basically, we do need to enter all the dead loads and live loads along all the three directions. So that is the thing, that is the way things work in the start software. So you do need to do that only. So we can go to this area here. As for remembrance, we can just enter the star here. After that, we do need to enter the member load here. We can enter uni gx 15.3. After that, we need to enter uni gy 15.3 and then uni gz 15.3. Same we can do for the next load case also. So we can enter uni gy here and uni gz here, and similarly for this member loading also, uni gx 4.5, uni gy 4.5 and uni gz 4.5. And after that, we do need to enter the flow loading also in all the three directions. So we can enter uni this to classroom gx here. You need to note that this is the dead loading that we are applying in all the three directions. And here also we can see that the group command, how much it helps, as the syntax is very small in the length. So you can easily just copy paste them, and it is also easy to remember that on what level we are working and what exactly we are doing. Otherwise, if you refer to if you are comfortable with the coordinates option for the flow loading, then you can think of how much time it will take for us to do the dynamic analysis. There, I must say that there are other ways also to do the dynamic analysis. This is not the only way. Some people, what they do is that they apply the pinned support on all the nodes and then calculate the loadings, and then they apply that on the structure. See, I am not comfortable with that approach. So cause in the case of any revision, what we need to do is that we need to repeat the whole procedure again. But with this approach, what we can simply do is that we can just go to the editor file and then just copy paste the change loading in the form of this particular arrangement here. So as for different engineers, the perception is different. So I'm not challenging anyone that this is the only method, but what I am saying is that this is the easiest method with which we can solve our problem of dynamic analysis. So as for this live loading, what we need to do here is that we do need to reduce the loading also. So we need to enter 0.75 here. As we are comparing with like the static earthquake method, so there's no logic in applying the full loading here. We do need to take the 50% loading only for the values that which are higher than the 3 kN per meter scale. %25 of 2 is 0.5. Gx, Gy and Gz, and we do not need to take the terrace loading. So now we have defined all the loadings for all the 3 directions here, and we can just switch off this editor file here. And when we go to the reference loading definition here in the mass source, we can see all the loadings that we have defined for our structure. So now we are done with definitions also. We are done with the load case details also. And now we are done with the analysis part also. So we have defined the supports, we have defined the specifications, we have defined the materials, and let us check that whether all the properties have been assigned or not. So as we have defined some new beams in our structure, so we can just assign them a property here. For beams, we have typically assigned 230 by 600 size. So we can go to select by missing attributes and missing properties, and then left click on assign to selected beams and yes. So now everything looks fine. And before, in like what my practice is that before I design, like put all the design commands here, what I usually do is that I analyze the structure first, so that I can detect all the errors in our structure. So go to analyze and run analysis. So there is this one error here. So basically it is saying that no reference load case of type, mass or gravity dead or alive is defined for mass modeling. Center of mass calculation is not possible. Basically the problem here is that the mass loading is already defined, but it is defined after the flow diaphragm. So in this case what we need to do here is that, so we go to the editor file here and we search for the reference loads here. So here we can see that the definition of the reference load is coming after this seismic weight, and the STAD has stopped working around here. So what we need to do is that we do need to shift the reference loading before the flow diaphragm option. As technically also you cannot calculate the flow diaphragm before like without defining the mass source. So we select the option from define reference loads here, and select cut all these commands by pressing Ctrl plus X option on my keyboard, and then we can go to this space here, that is before flow diaphragm. Just press Ctrl V option on a keyboard and just save the editor file here. Now we can see that the reference loads are still available here, so that is not an issue. And if we analyze the structure again here, yeah, you need to ignore this warning. Basically what happening is here is that we have not entered any data for the vertical earthquake load cases here, so that is why this warning is being shown. So now we can see that the stat can now process the file, and now it can analyze the structure. So now we can see that the stat is showing us 2 warnings and 6 nodes. So let us check that what exactly are 2 warnings and 6 nodes by pressing view output file option. And here we can see that mass model formed will be using the seismic response time history analysis. So you need to ignore this warning. This node you can also ignore. This node you can also ignore. This is an important node here. That is for this horizontal earthquake. The multiplying factor is 4.3021 here, and for along Z direction the pattern here is the scale factor required is 5.0435. How I'm guessing, how I'm saying that for X it is 4.3021, because it is written after this time factor for X1893 loading. So if you want to understand what exactly is being written here, so here we can see that the unit is kN meters. Time period as per 1893 that we have entered manually, that is 0.187, and for this value the SA by G value is 2.5, and the factor V, that is Z by 2 into I bar into SA by G, it is coming out to be 6%. That is 6% is the base shear value. And here this is the warning here. So it is saying that some modes are closely spaced, so CSM methods of model combination should be adopted. So we can left click again here. So instead of SRSS we can select CSM here. And instead of this here we can select CSM method here. And again we can analyze. And if you want to see the mode shapes also, we can go to post processing here, left click on OK. We can go to dynamics here and then modes here. So if you want to see the first mode shape here, this is basically going in along the X direction. If you want to see the animation also, left click on animate here, left click on mode here, and then left click on apply. So here we can see that the first mode is translation mode along X direction, and here we can select the mode 2 also. So mode 2 is somewhat torsional. So here we can see that the mode 2, the structure is being rotating about this point, and mode 3 is pure torsion. After that mode 4 zigzag, mode 5 and mode 6. And if we want to check that whether we have achieved the correct results or not, we can go to mass participation factors here, and here we can see that the mass participation is not more than 90% here. Ideally for this type of regular or general structures, we should target for mass participation for more than 95 or 96%. And for along X also the mass participation is not good. So what we can do in this case is that we can go to commands, this miscellaneous, and here there is an option to enter the to increase the number of modes. So here we can see that for maximum number of mode shapes are given as 6, so we can enter here as 20, and left click on OK here, and then again we can analyze the structure to see that whether we have now increased our mass participation or not. So we go to the output file here, and then we can check the participation factor. So here we can see that now we are getting the participation in the terms of 93 and 92%, and the number of modes initially we were shown only as 6, and now that has increased to number of modes as 20. And similarly for the along X also, for RSX, the mass participation in the range of again 94% and 92%. So 94 and 92 are not that bad, but 80 less than 90 is not desirable. Less than 90% mass participation is not desirable at all. So now we are comfortable with the system, we are comfortable with the dynamic behavior also. That is for mode 1, and this is for mode 2, and this is for mode 3. So similarly we can check the dynamic behavior for all the modes here. And now in the next lecture we shall learn how we can finally design our structure, and to design, what are the design commands and what is the procedure that we need to follow. Now we have almost done everything in the structure, right from modeling, and now we have done the dynamic analysis also. Now we need to do our second last step. That is, second last step is how we can design the structure, and the last step is how we can detail the structure. So doing the second last step, what we need to do is that we need to go to design, and here we need to select the concrete here. So current code, we can select it as IS456 here. If you are working with American standard, you can refer to ACI 318 2011. The only difference is that if we are selecting IS456 here, the parameters shown will be different here. So for column, let us say the cover is in the range of 40 mm. So we can enter 40. For beams, let us say the cover is 35 mm. Cover by cover I mean clear cover. And after that we can enter the grade of concrete as M30, that is 30,000 kilonewton per meter square. The grade of shield we can enter it as 500 grade, that is 1 tens 100,000 10,000 lakh 5 lakh kN per meter square. Similarly we can enter the same value for Fy secondary, and if required we can enter this max main and max secondary, but practically I don't use them. And this is also mmac command. Mmac command is the command which some people do use it. The reason for using this mmac command is that the stat considers the bending moment from joint to joint, not from face to face. That is, if if this is a column and this is a beam, so this column must be having some thickness here, let us say 600 mm. So the moment that shall be considered by the stat shall be at this joint only, not after 600 mm. But the advantage of using ETABS and SAP is that it considers the face moment, not the joint moments. So this is also one disadvantage. So that is why the reinforcement in the stat is always on the higher side as compared to the ETABS and SAP. And here we can have a track command also. So with the help of track command you can get a detailed design report for your structure. So clear 0.04, we can go to select beams parallel to y-axis to select all the columns at once, and then similarly we can go to select beams parallel to x and select beams parallel to z to have beams selected for horizontal directions. We can assign FC30 to the whole view here, and similarly Fy mean of 500 to the whole view here. And after that we can go to command section here. We can left click on design beam and design column here. So we can go to select beams parallel to y-axis here to select all the columns, and we can go to select beams parallel to x, select beams parallel to z to select all the beams here. And after that we can also have a command of takeoff. So takeoff is a command which calculate all the concrete and steel that is being used in your structure. And after that we can go to analyze and again yes. So now we are not worried about this scale factor or the number of modes with which we do need to have. Or the warnings that we are getting here is are the number of beams and columns that are failing in your structure. So designing structures are always interesting, like if you are new to this field, you will find it amazingly satisfying to like design the structure, and when the building is constructed you will be amazed to see and you will be proud to like what you have made. So this is also work of like very high responsibility, that you do need to take care of what exactly are the risks that you can take, etc. And here we can see that in the warning section it is showing that some columns are failing in the design. So only 5 number of columns are failing here, and length to depth ratio for this beam here, for that inch and wrench parameters need to be designed, and these two parameters are the most confusing parameters in the STAAD software. To to tell you the truth, I also don't know them how to apply them correctly, and if although I can apply them, but it do happens that every structural engineer has its own perception regarding this inch and wrench parameters. If you want to study about them, you can go to the help file here on your computer screen, and you can go to contents and study about the inch and wrench parameters. But as per my opinion, this warning is null to void warning. You don't need to worry about this warning. So only taking care about these columns here. So column number 335 and 332, 156 and 86. So 335 we can go to list beams, we can select 335 here. So in the plan, this is the column. So here we can see that these two columns are failing, and this column is also failing. So we can see the behavior here for this column here. Basically, before correcting the results, I want to give you a brief preview of what exactly, how are the design results of beams and columns shown in the STAAD software. So we can go to, let us say, this particular floor here. So we can go to view selected objects only. So here we can see that, or we can to make the things clear, I want to explain you in the isometric view here. So here we can see that this is, let us say, a beam from this point to this point. So if we select the 1.5 times dead load plus live load combination here, and open this bending moment MZ graph here. So here we can see that the bending moment is negative on this point and this point here. So here we can see that this is the graph, and bending moment is positive in the center point. So if we left click here and we left click on concrete design here, so here we can see that the bending moment that is negative value is in the range of 223.41, that is at this particular point, and bending moment is negative here, positive here, and the value is 88.21. And before doing that, there is this one thing that we are missing in our design. We have not applied the load list command. I've been working on the STAAD for more than 10 years, and I want to confess that I always just did this mistake. So we need to go to perform analysis, and we need to go to load list, and we do need to select the load list as 20, right from 201 to 281. Basically, how I caught that, why I have not applied the load list command, because the beam was being designed for this particular load combination here. So here we can see that for this load combination, the beam do not needs to be designed, as this was just a pseudo load combination, and beam needs to be designed for all these load combinations here. So to explain that to the start, we do need to apply load list command here. And again, we do need to analyze and design the structure. So that is why I always prefer to go with the like a checklist method. That is, each and every step like you should keep an Excel file, and whenever we are doing a particular step, just tick in front of that, so that no step is missed in your designing. I've also seen some engineers missing the self-wait commands here. This is the truth that I have seen many new engineers, they do not apply the self-wait command in the structure. So that can be a very risky. So yeah, I shall always request you, or I shall always advise you to go with a particular checklist pattern. Create a checklist and always follow that checklist to design the structures. And now we can see that the same beams are now failing again in the design, so that we don't need to worry much about the failing sections here. Before that, I want to move to the same section that we were discussing earlier also, that is the design commands and how we can check the design results. So we can left click on this 1.5 dead load plus live load and select MZ value here. So this is the bending moment diagram for this particular load combination here. And if we want to see the bending moment diagram for some other, here we can see this is the bending moment diagram. So keeping the thing simple for the gravity load combination here, when we left click here we can see that the maximum negative bending moment is 223.41 at this point, and maximum positive bending moment is 79.67, that is at this particular point here. And similarly, if we want to see the design for this particular beam here we can see that the maximum negative bending moment is 227.4 at this particular point, and maximum positive bending moment is 181.3. So the thing is, okay, this is the bending moment diagram for which it is being designed. These are the parameters that we have entered. That is, the size of the beam is 230 by 600, length of the beam is 2.5 meter, that is from this point to this point. The grid of concrete is M30 and grid of steel is 500. And this is the basically the area of reinforcement that is being shown here. So it is saying that as per the tentative, or we can say the conventional detailing as per the IS456, the area of steel required is 360 in dia on the top here, and 660 in dia on the top here, and bottom we can have with 8 number or 12 dia bars. Although in 230 mm width we cannot accommodate 8 number or 12 dia bars. So that is just altogether another different approach. So that is why we do need to understand the detailing that we need to do in our structures. So this was just a typical explanation of how we can check what the magnitude of bending moment. And for some people who want to cross check the results manually also, they can refer the results from here, refer the results of bending moment from here, and then they can cross check the results. So this was for the beam design. After that, if you want to see the column design, left click here. So here we can see that for 350 by 350 column, the load case that is governing the design is 218, that is 1.5 times dead load plus 109, that is plus RSZ plus 0.3 RSY plus 0.3 RSX. And the bending moment is somewhat biaxial. The reason for biaxial bending moment is because we are considering the response vector load along both the horizontal directions. So that is why you will see that most of the columns have both the bending moments, that is minor as well as along the major axis bending moment. So here we can see that the minor axis bending moment is very high, in the range of 88. So coming back to this column here, so this is basically the bending moment along the major axis as well as along the minor axis, and Fy is 500, Fc is 30. Area of steel required as per the design is 18.23 centimeters cube, and area percentage is 1.6. So the bar size that tentatively is being shown by status 4 number 25 dia, but that we can change. So how like there is a relation between 425 dia and 1823. I need you to explain this short math here. Basically, you do need to remember the area of the steel bars. That I will explain in the detailing lecture also, but to give you a brief preview, if we want to calculate the area of the, let us say, 12 dia bars, so what we need to do is that 3.14, that is pi into d square, that is 12 divided by 4. So this is the area in mm square. So 12 dia bar area is 1.13 centimeter square. That you do need to remember. After that, if you want to calculate the area of for 16 dia bar, that is 200 mm square. How? That is 3.14 into 16 divided by 4. So here we can say that this is 200 mm square or 2 centimeter square. After that, if you want to calculate the area of 25 dia bars, so 25 into 25 divided by 4. So it is 5 approximately in the range of 4.9 centimeters square. So 4.9 into 4, it comes out to be 1962. So the area of steel required was 1823, but if we provide 4 number 25 dia bar, we will provide 1962.5 mm square. Now if we want to see the detailed design of this particular column, that is beam number 167, we can go to the output file here, and we can search for 167 here. So this is the column number 167 here. So the area of steel required was 1823, okay, and we have provided 4 number 25 dia bars. So basically you will see two sections here: section capacity based on reinforcement required, section capacity based on reinforcement provided. So based on reinforcement required, the value of the bending moment that we have earlier studied also, it was 113, and this PU was 2312, and interaction ratio was 0.99. Now if we provide 4 number 25 dia bars here, the capacity shall be 132, that is bending moment along both the directions against 113.64, and PU value against 2312, the capacity shall be 2363.55, and interaction ratio shall be against 0.99, it shall be 0.79. So that is why I always recommend you to provide reinforcement on the higher side only, because that will lead us to somewhat higher factor of safety as compared to the design. So that is why it is not compulsory that if the area of steel required was 18.23, you do need to require exact 18.23 centimeters square. There is no harm in providing 4 number into 25 die, that is 1963.5 mm square. So against 1823 we can go to 1963 or 2000 mm square also. So that is all the decision of the structural designer. And similarly, if we want to see the beam design of a particular like let us say if you want to see the beam design results here, so here we can see that 551.49 mm square is the requirement on the top, on the starting point, that is 0, and on the end point, that is 3.5, it is 4.33 centimeters square, and bottom again the requirement is higher here and somewhat lesser on this particular point. So that is why it is showing the detailing as 3 number or 12 dia bars, and on the bottom, and on the top it is showing as 5 number 12 dia bars. So that I will explaining the detailing, that how we can detail a particular beam. So you cannot provide this 2 leg data 165 mm center to center in your structure, because this is not as per the detailing standard, that is IS13920, that was released in the year 2016. As per the 2016 code, we cannot exceed the spacing of the the stirrups by some parameters that I shall be explaining you in the later lectures. But the focus of this lecture was just to make you familiar with how we can see the design results, how to interpret the design results, and what exactly is the way with which you can calculate the area of the bars. So I hope the things are now clear to you. That is how we can proceed to the designing of these particular structures here. And going back to the columns which are failing in the design, the numbers were this 86, 156, 332, 334 and 335. Now we can close the Outlook file here, and then we can search for the beams that are failing. So we can go to select by list and beams, and here we can enter first of all 86. So this is the column here. After that we can go to 156, so that same column. So basically this column, and this column is showing problem. So we can select these particular columns here. We can press Shift plus B option on our keyboard and select beams parallel to y-axis, view selected objects only, remove the dimensions. So now in our structure the beams were 86, that is this particular column, 156, that is this particular column. After that 332, 334 and 335. So by default the sizes of these beams were 2, that is 350 by 350. So we can increase the size of these particular columns to 350 by 600 mm. Although we do need to take care of the architectural drawings, that we can try increasing it to 400 by 400 mm also, or 500 by 500 mm also. But that optimization you can also do at your side. And to reduce the time of this lecture, we can just increase the size of this column to 350 by 600 mm. And after that we can again analyze and design the structures. See, optimization is another the thing that you can understand by practicing on your own. I cannot tell you, or I cannot share you how you can exactly optimize the structure. I can share you some tips, or I can share you some insights, but you do need to practice on your own only to understand how we can perfectly analyze and perfectly design the structure. For a structural engineer, the most difficult task is to create a balance between the resources that is being put in on the structure and the optimization of those resources. So let us check that whether these columns have passed or not. So now we can see that all these columns are now passed. And if we want to see the warnings here, so only length to depth ratio warnings are being shown here. And if you are very resistant to remove these warnings also, then you can go to F5 sec here, and you can range parameters here. Let us say the range length is 0.5 here, so left click on add here. So the beam number is beam number 8, 148, 297, 299, 475, 641 and 814. You can prepare a checklist of these members: 8, 148, 297, 299, 475, 641 and 814. Select all these beams here, and we can enter these beams here. So 8, 148, 297, 299, 475, 614, 641 and 814. Now we can again analyze the structure. So now we are done with like modeling. Now we have understood how we can analyze the structure, and now we have done like understand how we can design the structure. Now in the next lecture we shall learn how we can do the detailing of the structures. So I shall be explaining you some typical beams and some typical columns also, and I hope that that shall help you to give you a clear idea of how we can do the detailing of the RCC structures. So in the previous lectures, we have learned how we can analyze, how we can model, and how we can design the structure. Now we will move on to how we can provide the reinforcement so that the civil reinforcement drawings can be made and the work can be done on the site. So first of all, we shall start with the bottommost point. That is, we shall start with how we can design the foundations. See, foundations are the structural elements which are basically responsible for transferring the whole superstructure load to the earth. So that is why the shape of the foundation can be either rectangular or it can be square. But in the areas where the bearing capacity is not good, so by like by the line that the so if the bearing capacity is not good, it means that if let us say the bearing capacity in the range of only 5 ton per meter square or 50 kilonewton per meter square. So in that case, what may happen is that the structure may have excessive settlement if we provide isolated footing or a pad footing. So that is why we do need to provide in that case pile foundation, or we can also go for the raft foundation. So that all like recommendation is present in the geotechnical report of a project. So before we start the designing, the soil consultant must have done some test on the actual soil, and he shall always provide you with the geotechnical report, which shall always have a recommendation that what kind of footing shall be adopted in this structure. So coming in our case, let us say the bearing capacity of the soil below this like footing is in the range of 25 kilonewton per meter square. So if we are saying that, let us say the bearing capacity is in the range of 25 kN per meter square, so it might happen that for some footings we might need to have an isolated footing. For some we might need to have combined footing also. So let us suppose we collect all the joints here. So in this area we can see that some joints are very near. For example, let us say this 2.5 meter is very nearby to each other. So if we shall design the footing for these two columns here, it might happen that the footings may overlap with each other. So we may recommend a combined foundation in this case. And for this case, as the spacing is very high here, so for all these columns we can provide an isolated footing. So and there is this one most important question that is most widely asked, that what exactly are the scope of the service load combinations and what exactly are the scope of the strength load combinations in the foundation design. So all these load combinations are the service load combinations here, that is only one times factor, and all these load combinations are the strength load combinations. So for strength load combinations basically used in the design of the reinforcement, and service load combinations are used in the design of the size of the foundation. So In our case, let us say we start with this particular joint here. So if we go to the post processing mode here, we shall first of all select the only the service load combinations, because first of all we need to finalize the size of the foundation. So we shall select from 301 to 357, left click on apply, and we shall go to the reactions here. So in this case you can see that there is this very dense window which are showing all the reactions here. We can go to results, view value, and remove all, so that we can see what kind of nodes are we working on. So we can select shift plus K option on your keyboard to highlight the joints here, and shift plus S option to switch off the supports icon. So let us say we first of all start with this particular joint. So the joint name is 77 here. So if we select this joint here, automatically the this particular node number options will open. And as we have selected from 301 to 357, so only these particular values will be highlighted here. So the maximum fy value that we can see here, or what we can do in this case, is that we can just select all the cases here. I'm expecting that you must have basic knowledge of MS Excel, because teaching each and everything like Excel or in like PowerPoint is difficult for me in this lecture. So let us say we copy all these loads here. So in this case we have all the this is fx, this is fy, fz, mx, my, and mz. Let us open the Excel file here. So here we can see the fx, fy, fz, and mx, my, and mz. So in our case, we can see what is the maximum value of vertical reaction here. So we can write an equation here that is equal to max bracket here, and then we can scroll all the way to the topmost cell. So this is the vertical maximum vertical reaction that we can expect here. And if we want to see the maximum moment here, so this is the maximum bending moment, and we can similarly check maximum bending moment along the m for mz also. And fx and fz are nothing but basically the horizontal forces that are acting on the at the support level. So if we want to see that in which case this like maximum vertical action is coming, so here we can see that for load case 344 and load case 342, the value is almost same. So for all the other cases, the fy value is the maximum, that is a vertical reaction that is acting at the support level. So we can expect that the dominating axial force is this particular value. So we need to check the foundation for this particular load case, that is the maximum vertical reaction. And after that, for maximum bending moment, the value is 137.634. That is also for the same particular load combination. So in the basic Excel file, we can enter 1027. The actual load is 1027.755. So first of all, we start with this basic Excel file. So before starting, I must say that this is not my Excel file. So this Excel file was available free of cost on the internet, and after reading the source code, I can see that this this Excel file is correct as per the Indian design standards. So first of all, let us say the grade of concrete and foundation is M30 only as per IS456. Steel grade is Fe500. Axial load that we have shortlisted is approximately 1028. So we can enter 1028 Kn value here. After that, My and Mz. So now we have basically two bending moments here, one for 137.634, and for this particular load combination only, the bending moment along the other direction is 29.906. So we can enter 138 and 30 here. So before, you should understand what exactly is my and mz. So here we can say this is the my axis. So the major axis bending moment is my only, and the minor axis bending moment is mz, that is 30 kN meter. The column size which we have considered here is approximately 350 by 600 mm only. So we can enter column size B as 600 and D as 350 here. SBC of soil is 250 kN per meter square. Design factors, as here in this Excel file we have considered only the service factor combination. So here we can enter the required all the combinations to be multiplied by 1.5 to design the reinforcement here. So the axial load that is being considered is here the same value. The self weight of the foundation is also a very important concept here. So self weight means that the footing self weight and the weight of the like soil or extra thing that can be like putting pressure on the soil. And after that the total weight is approximately 1130.8 kN. Area of the footing is a very important concept here. So the area of footing is nothing but this value multiplied by this value. So all these are the cells that you need to input here, and these two cells are also the cells that needs to be an input here. So basically we do need to have the area of the footing such that the total bearing pressure is less than the bearing capacity. You should understand this very important concept. People always get confused here. There are two things. One is the bearing pressure, other is the bearing capacity. Bearing pressure is the one that is being applied on the foundation bottom here cause of the load acting on the top. And bearing capacity is the maximum capacity of the soil below this footing here, so that the permissible settlement does not exceed. So we come back here. So basically the size of the footing right now we can have, let us say we want the size of the footing as 2.5 by 2 meters here. So the footing pressure maximum is in the range of 289.84 kN per meter square, but our maximum SBC of soil is 250 kN per meter square. This size is not correct, so we can go up to 3 meter by 2.5 meters. So now we can see that there is no extra margin here. So as compared to 250, we are only getting 183.47. So that is somewhat wastage here. So what we can do, let us say we can go by 2.5 by 2.25 here. Then also there is a warning. So 2.75 by 2.5. So in this case we can see that uh, now it is somewhat okay. So against 250 we are now getting 227.73 kN per meter square. So this type of like difference is manageable and desirable also, but otherwise as compared to 250 we only give footing pressure of 150, so that is a highly over designed foundation. So now we can stick ahead with 2.75 by 2.25 meter foundation. And if you want to like design the reinforcement here, so for flexural design, the reinforcement needs to be checked. So for flexure here, we can see that the area of steel requirement is coming out approximately 1175.8 mm square per meter width. So either we can go ahead with 12 dia. So 12 dia 100, we can see that only 1017 is there. If we or what we can do here is that we can also increase the foundation depth. So right now the foundation depth is, we can provide it to be 550 mm. So for 550 mm we can see that the area of steel requirement that is coming here is approximately in the range of 1375 mm square per meter width. So we can increase the diameter of the bars here, so we can provide 16 dia 125 center to center. So in this case, against 1375 mm square per meter width, we are now providing 1447 mm square per meter width. So this is also an input for you, and after that we can also check for the shear values. So basically two types of shear acts on the footing. One is the one-way shear, which acts at d distance from the face of the column, and the other shear is a punching shear, which acts at d by 2. By d I mean the depth of the footing, not this small d, that is the size of the column. So here we can see that the d value is nothing but the total total depth minus the cover of the footing. So here we can see that the reinforcement that has been provided is approximately 16 by 125, and in the other direction, let us say if we want to see the requirement, so the requirement is coming out in the range of 1200 here. So against 16 dia we can provide it to be, so in the longer direction, you should understand this point. So in the longer direction always the reinforcement shall be higher, and in the shorter direction the footing reinforcement shall be lower. So you don't need to get confused here. So basically if this is the longer side, so 16 by 125 shall be provided here because the cantilever distance is more here, and if this dimension is less, the cantilever distance is also less, so the reinforcement requirement is also less here. Basically the cantilever moment that we are calculating here is nothing but WL square by 2. So we calculate a W, that is the pressure that is acting on the foundation, and L is the nothing but the cantilever here. So this is the projection that is being that is here, this B1 here. So as I was telling you earlier, that W into L square by 2, that is B1 square divided by 2 into W, that is the bearing pressure that is being coming on the foundation bottom. So this is just a simple science that we are doing here. I will again repeat all this concept. First of all, you need to understand the difference between the bearing pressure and bearing capacity. Bearing pressure is the one that is like coming on the foundation bottom, and usually it has the distribution diagram like this only. Bearing capacity is the one that is given by the soil consultant, and it is like 15 ton per meter square, 20 ton per meter square, 25 ton per meter square. So it all depends on that. After that, the basis of the design, that is a factor which goes the foundation design. Number one parameter is the one-way shear, and which acts at distance of d, two-way shear which acts at distance of d by 2, and the design as per the flexural requirement, that is the bending moment, as and the bending moment that we consider is the cantilever bending moment. So that is why we always provide the more number of bars on the longer side and lesser number of bars on the shorter side, because the if this projection distance increases, the bending moment also increases, and if bending moment increases, the area of steel requirement also increases. So we can sum up here that we do need to provide here this 2.75 by 2.25 meter foundation here. So we can go to AutoCAD file here. So here we can enter the F1 sizes 2750 mm, and the shorter dimension is 2250 mm, and the depth requirement that we are getting here is 500 mm. So bottom bar that we need to provide along the longer direction is 16 dia 125 mm, and the along the shorter direction we need to provide 16 dia 160 mm. So this is basically the typical section of the foundation that we can follow here. Now there are two approaches again. The some people like want to design this as a sloped footing. Some people want to design this as a pad footing. So in this case, let us say if we want to design a pad footing, so what we can do here is that we can just make this foundation as a pad footing. So this is just a simple pad footing that we have drawn here. So in this case, this is basically the 500 mm depth here, and the area of steel that is like the main bar is 16 die 125 mm here, and the shorter reinforcement bar is 16 die 160 mm here. And most of the people are like, why we do not provide the this reinforcement on the top? Because we don't really need the this reinforcement bars on the top face. So if you are very much like typical or like conservative about all this concept, then what you can do here is that you can provide a nominal number of bars on the top. So let us say we can provide 10 dat 250 mm bars on the top. So that bars does not have any structural significance, except for they may act as a temperature reinforcement or skin reinforcement. But otherwise in my career, I have not seen anyone providing this top bars on the for the footing top, except for when we are designing the combined footing. So in the combined footing, they are really required because the bending moment profile may come on the top here also. So the most important concept that you do need to understand for any foundation design is to like imagine how bending moment will travel and how what will be the pressure distribution diagram here. So it's like in this case, the maximum footing pressure is 227.73 and minimum is 104.55. So in this case, what basically will happen is that the moment will not travel, the pressure will not travel at the top. So if we want to, like draw the pressure distribution diagram for this particular two values here, so what we can do in this case is that the pressure distribution diagram shall be nothing but it shall be just a simple trapezium. So in this case, the value here shall be 104.55 and the maximum value shall be this 227.73 kN per meter square along this face. So this is just like your understanding that you should understand if this value is positive, then pressure is not going on the top. If this value is negative, then the bending moment pressure is going on the top and there is a tension on the footing face. So if there is tension in the footing phase, then you don't need to worry about that, but you just need to take care that this is just a thumb rule, that at least 75% of the footing is in touch with the soil, because otherwise if this whole area loses the touch with the soil, then there might be a risk of the sliding and overturning also. So I hope now you have understood how we can design a simple isolated footing, how we do need to check about the basic concepts, that is how we what is the importance of the SBC, soil bearing capacity, what is the importance of pressure distribution diagram, what is the importance of bearing pressure, one-way shear, two-way shear, or flexural design. I cannot go into much depth here because otherwise the uh, length of this course shall be very long, but you can refer a basic textbook here. And as I had explained you about the basic concept, I hope that you shall not face any problem in understanding all the technical terms that are being used here. So in the next lecture, we shall learn how we can design the combined footing for this for these two columns. And combined footing is itself a very important concept that can be a nightmare for the beginners because they don't understand all these things, that how we can distribute the uh, combined footing reinforcement, and most of the textbooks, if you refer, they don't guide you correctly also. So the next lecture I shall try to simplify all the combined foundational things so that you may easily get a grip of how we can design them easily. So in the previous lecture we have learned how we can design the isolated footings. So in the previous lecture we have tried to design the isolated foundation for the joint number and 77. Similarly, we can design the foundation for all the above nodes here and all these nodes here. So I won't take each and every node design, but you can do that on your own, and I have attached the Excel file for a reference also. And in this lecture we shall try how we can design the combined foundations also. So combined foundations, number one, why do we need to provide them? Because basically what happens, for example, let us say in this case we try to design the foundation for joint number and 79 and joint number 99 individually or isolated foundation. So what basically will happen in that, let us say the foundation is coming like this. Okay, so and if we try to design the joint number and 99 foundation, it will come like this. So basically both the foundations will overlap with each other. So to avoid this type of scenario, what we can do is that we can just design a simply combined foundation for this type of cases. So similarly we can design a foundation for these two joints also and these two joints also. So coming back to this particular these two particular joints, that is joint number 79 and joint number 99, we need to go to the post processing here. After that we need to select the service load combinations here, that is from 301 to 357. Left click on apply and OK. Now if we go to the reactions here, we can go to results, view value and remove all to see clearly where exactly are our joints here. So we left click on joint number 79. So when we select the joint number 79 here, all the service load combinations and fx, fy, fz, mx, my, mz values will come. So basically fx is horizontal force, that is the force that is acting along this direction. Fy is the vertical force, and if Fy is positive, then it is a compressive force, whereas it might happen that in some cases Fy is negative also, then basically the footing is completely in tension. So this is also a mistake that most of the new engineers do. What they do is that they simply ignore the negative sign and they take the positive sign for the design. So that can lead to catastrophe, as your footing can be tension and your footing or the structure may simply overturn in that case. So Fz is nothing but the horizontal force along z direction. So if this z is minus here, so it means that it is not acting along from this point to this point, it is acting along this particular direction, that is from this point to this point. And mx, my and mz are nothing but moment along z x-axis, y-axis and z-axis. So basically my is nothing but torsional moment here. So that is why in all the cases you will find that my is of very less values. So here we can see that all the my's are nothing greater than 1 km only, and mx and mz are of some numbers. So basically mx is the moment along this axis and mz is the moment along this axis. So that is why you can simply ignore the my bending moment in the StatPro software. So coming back to the concept of combined foundation, we select the joint number 79 here. Here simply we can just select all these cells here from 301 to 357. Right click here and then left click on copy here. So here I have attached a this combined foundation Excel sheet here. So this is simply not my Excel file, but we can just copy and paste all the data here. So just press Ctrl plus V option on a keyboard. So here we have now entered the data for joint number 79 here, and after that we need to select the data for joint number 99 here. So we select all the cells from 301 to 357 for joint number 99, left click on copy, and we select copy paste all the data here. So this is basically the input sheet here and after that we need to go to CF1 here. So this sheet has basically the simple Excel file for design of the combined foundation, and basically what the problem, why we have not directly enter the data here, cause this file can needs to have the data in the ton and meter. So in here all the data is in kilonewton. So we need to have basically direct relation between this file and this file. So if you left click here, you will see that the value that is being copied here is divided by 9.81 for the value here. So all the values that are coming here is in ton and meters. So here we can see that, for example, let us say for 301, force Fy is 103.294 and the force here is 1013.317. So if we divide this value by 9.81, you will get 103.294. So similarly, for the data is automatically copied for joint number in 79 and joint number in 99. So basically why we are comparing both the cells. So it is a very basic thing to understand. Basically, if these two columns here, the vertical load is acting on these two particular columns. So if this whole pad should have that much particular area, so that it get passed in the bearing pressure calculations. So for example, let us say the column load coming here is approximately 100 ton. The column load that is coming here is, let us say, 120 ton. So the total is 120 plus 100, that is 220 ton. Now our bearing pressure is bearing capacity is, let us say, 25 ton per meter square, or let us say 20 ton per meter square. So if the required area of the foundation is nothing but 220 divided by 20, so the required area of the foundation is 11 meters square. So we can provide either 3 meter by 4 meter foundation. So the area in this case shall be 3 into 4, that is 12 meters square. Or we can also go with this 3 into 3.75 meter. So in that case the area shall be 11.25. That is higher than this required area of 11 meters square. So this is just a simple thumb rule calculation that you need, or that is required to do before you conduct the final design. That is, just calculate the total load, consider the bearing capacity, divide the total load with the bearing capacity to get the required area of the foundation. So these are just the simple thumb rules that we used to study in our college also. So coming back to our scenario here, basically what now we need to do here is that we do need to add this value with this value, so that we can get the total P by A, and we also need to consider the M by Z values. So with this we do need to calculate P by A for both the for both the columns, and M by Z for both the columns, to get the required bearing pressure. So you might be getting confused here because you have not gone through all the calculations, but I will simply explain all the steps one by one. So you must have got the simple concept of the required area calculation for the foundation. After that, you can enter the data here, as I had explained you earlier also, that we do need to divide the total the values that have been input here with the 9.81 to get the units in ton and meter. After that, we do need to enter the required data here. So in our case, the distance between the two joints is 2.5 meters here. So we can enter 2.5 here. After that, we can select the offsets here also. So let us say we select the offset 1.25 meters here. After that, our column is 350 by 600 mm, and this is nothing but 1.25 plus 1.25, that is 2.5 plus 2.5 meters here. So after that we can enter the the depth of the foundation also. So right now indicatively we can select 700 mm depth of the thickness of the foundation, and depth of the foundation can be considered as 2.5 meters here. So here in the previous Excel file we have considered the depth of the foundation. We have not considered basically depth of the foundation, but we have considered the bearing capacity. So the bearing capacity that we have considered is 250 kN per meter square. So in this Excel file you will see that for the bearing this SBC values, you will see two values here. So basically the thing is that as per the this IS1893, you can increase the bearing pressure for the footings. So for rock and hard soils, the percentage increase allowable is 50%. For mediums or stiff soil, it is 25%, and for soft soil there is no 0% increase allowable. So if for example we are as per the soil report, we have bearing capacity of 20 ton per meter square. So 20 into 0.25, that is 5. So 20 plus 5, that is 25 ton per meter square is the allowable bearing capacity for medium or stiff soils. So basically here we have considered directly 250 kN per meter square, considering the original bearing capacity was 20 kilonewton per meter square. So 20 into this 1.25 is 25 ton 25 ton per meter square. So that is 25 ton per meter square is nothing but 250 kN per meter square, rounded off. So in this file, when we consider the gross this SBC as 20 ton per meter square, we can consider it to be this 1.25 times of 20, that is 25 ton per meter square. So we can most of the people do get confused in net and gross this SBC. So to avoid that confusion, I am just deleting this row here. So this is nothing but 20 into 1.25 here. So when in the case of the wind and earthquake only, this increase is allowable, but not in the case of gravity loadings. So here also, as we were seeing that the wind or earthquake load was dominating the design, so that is why we have increased this SBC. So here also considering SBC is 25 ton per meter square. So now the shape of the foundation is rectangle. As the length of the foundation, we can see that 5 plus 1.25 plus 2.5 plus 2 times 1.25. Width of the foundation right now can be considered as 3 meter here. Thickness of foundation, as we have discussed, 0.7 meter. Founding that 2.5 meter. Length of the this column was 350 by 600 mm. So section modulus is nothing but BD square by 6. So for example, let us say you have this rectangle here. So for example, if you have a rectangle here, so let us say if this is B and this is D, so the section modulus is B into D square by 6 for this particular axis, and it gets reversed for the about the inverted axis. So if we are talking about this, so B into D square by 6. So this is what it has been calculated here. You can also, if you don't have any clear idea about the section modulus and moment of inertia, you can refer to any basic structural analysis book to get the clear idea of it. And self weight of foundation can be calculated here. Self weight of soil can be calculated here. And we have now ignored the self weight of pedestal because the footing here is being casted at this particular level only. So here basically the level considered was 2.1 meter. So we can change it from 2.5 to 2.1 here. So the concept is that we have already taken the weight of the columns along this whole from this point to this point by the STAT software. So we don't need to take this self weight of pedestal. Buoyant weight, considering buoyancy is also a dominating factor when the groundwater table is above the foundation level. So most of the people do get confused for the buoyant weight also. So if your water table is like 10 or 15 meters below the groundwater table, so in that case you don't need to consider the groundwater table. But if your groundwater table is above the foundation level, then you do need to consider the foundation weight here. So if your footing has is is in a area where the water table is very high, that is above the foundation level, in that case you can consider the density of water here. Otherwise, please put it as 0 to consider the buoyant weight also as 0. So that is why these two weights are same here. And restoring moment we can just simply calculate here, and this is basically the data that has been entered. And now we have basically checking about again for the factor of safety against overturning and sliding. Basically these two factors are not that much dominating, but here we can see that for the sliding and overturning, all the cells are showing as safe here. But in this particular cell, for example, when we're checking about the bearing pressure, here we can see that this like if we were discussing about this earlier also, so this is P by A value, that is, and this is mx by z, and this is mz by z. And basically you do need to understand here, that is moment about x. We have added the moment about both the for the joint number 79 also, and for joint number 99 also. So here we can see that the moment is so here in this particular cell, you need to understand it, when we are talking about moment about x and moment about z, we are summing the mx for both joint number 79 and 99. Here we are summing the moment for moment along z, but for both joint number 79 and 99. After that, here we are summing the axial forces. So simply calculating P by A plus mx by z, and then this is nothing but P max and P minimum. So this is basically the allowable bearing pressure here. So the result is nothing but safe for this particular case. But basically the thing is that in the case of wind, we can have the increased bearing pressure here. So what we can do here is that we can just simply enter 25 here, or we can enter the formula here. So for all the cases where there is either wind load or earthquake load, we can use the increased bearing pressure values. So with this approach, you can see that now all the values are coming as safe here. So for the maximum pressure that is coming is in the range of 20.1, whereas allowable bearing pressure is in the range of 25 ton per meter square. So here also it is coming out to be approximately 22 ton per meter square against allowed 25 ton per meter square. Here this is in the marginal only, that is against 25 we only have this 24.41. So the maximum pressure is 24.408 and minimum is 16.412. So I won't suggest you to go to maximum margin here, because sometimes it do happens that your building may have some expansion, or the architect may say that your building needs to be considered for higher design values. So to avoid the end stage designing, what we can do here is that we can just simply increase this from 1.25 to 1.35 here. That will give us very higher design margins. So instead of 24.408, now we are getting 23.53. So we have now margin of 1.5 ton per square meter. And with buoyancy, it is nothing but same here. So here we can see that as our buoyant weight was 0, so both these values are coming in same here. After that we can check the bearing pressure at all 4 corners here. So this value is also 23.53 only. And after that we can check for the eccentricity with the buoyancy case. Basically this is basically the codal requirements, that the eccentricity should be L by 6, less than L by 6 and B by 6 for both the directions here. So we are now doing nothing but basically checking the P and MX and MZ, and after that we are calculating the eccentricity. Eccentricity for X is MZ by P, you need to notice this, and eccentricity for Z is MX by P. So with this we can just simply calculate the eccentricities here, and after that we do need to check for two-way shear and one-way shear only. So here we need to enter the limit state method, because nowadays working stress method is very rare. So we can select the concrete grade as 30 Newton per mm square. The length of the foundation is 2600 by 3 meters here. So basically this is the area that is being considered here, that is 5200 divided by 2, 2600, and 3 meter is this dimension here. Effective depth for 700 is 700 mm was the capital D, so we subtract the cover, that is 75 mm, so the effective depth is 625 mm, and maximum load on column is 124, so we calculate the punching shear to be 106 ton, and shear resistance of concrete is tau C is nothing but tau C into B into D, and we can calculate the depth required with this particular formula. It is coming out to be 263.7 mm only, whereas we have now provided the depth of 625 mm. So punching is not a problem here. So similarly we consider the one-way shear also. So percentage AST right now, that is this particular percentage here, it is 0.5 percentage provided. So we can simply check here, that is for percentage AST 0.5 here. This is nothing but table 19 of IS456. So against 0.5 Newton per mm square, sorry, for allowable shear stress 0.5 and K1 and percentage AST 0.51. So we go to this value here and M30 here. So for design shear strength of concrete is nothing but 0.5 here. So we can enter the 0.5 Newton per mm square value. So the depth required is 790 mm. So here we can see that the one-way shear is a problem here. So we need to increase the depth again. So instead of 700 mm, we can provide 850 mm here. So we do need to go through all the values again, that is whether anything is unsafe or not. So here we can see that instead of 23.53, now the value is increased to 23.65. So 850 minus 75 mm is 0.775. So we do need to provide somewhat higher dimension here. So we do need to increase the depth of foundation to some higher value only. So we can again check it to be 0.9 mm here. So for 0.9 mm, the percentage of AST is 0.43 here. So this is nothing but allowable shear stress is now somewhat reduced. So let us say it is 0.48 here. So 825 plus 75 mm is 900 mm. So now the depth required is comfortable. Or what we can do here is that we can increase the reinforcement here. So let us say we provide the this 20 dia at double layer of 20 dia 100 mm. So we can check it for this 50 mm. So what we can do here is that here we can see that percentage AST is 0.77 and for M30 it is the value is 0.59. So now the depth requirement are considerably reduced, that is 670 mm. So 670 plus 75 mm is 745 mm, but now we have provided 900 mm. So we do need to reduce the reinforcement here. So let us say we provide the spacing at 80 mm. So 20 dia 80 mm is again 0.48, or what we can do is that provide spacing 75 mm. Yeah, now the percentage of AST is 0.51, and for 0.5 percentage for M30 it is 0.5 allowable shear stress. So 790 plus 75 mm. So 865 mm is the capital D required, and we have already provided 900 mm. So now the one-way shear values are correct, and they are correct. And after that we also do need to check for the bending moment also, and minimum percentage of bar is 0.12% as per the IS456. So bending moments are not that much high, so the percentage of AST required, or the value of area of steel required, is lesser, and minimum percentage is higher. So basically the one-way shear reinforcement are governing the design. So we can provide 20 dia 150 mm 2 layers, and calculation of reinforcement at top. What we can do here is that the area of steel required is 511, and the required area is 1080 mm square. So we can provide this 16 dia 200. The area of steel is 1004, but we do minimum requirement is 1080. So we can reduce the spacing here. So now area of steel required provided is higher than the required area. So this is the final summary, that is length of the footing, width of the footing, and depth of the footing. So the top reinforcement is 16 dia 150, and bottom required reinforcement is 20 dia 115, 2 layers. So with this particular manner, what we can do is that we can simply design the combined foundation for any type of structure and for any type of joints. So as a trial, what you can do on your hand is that you can just pick up any, let us say you pick up 74 and 37 joint number, and then you can try to design the combined foundation. And I will suggest you to please go through the Indian standard IS456 to understand how and what are basically all the values here that have been considered, and what is basically one-way shear and what is two-way shear. One-way shear, as I had explained in isolated footing also, that it acts at distance of D, and two-way shear is nothing but acts at D/2. And I would suggest you to work with working stress method, because if you are working with very well-known renowned organizations, they won't simply accept the working stress method. Basically, as we have discussed earlier for the isolated footing also, then that how what exactly is the profile of the bending moment below the isolated footing. So basically, let us say if we are considering the isolated footing, the bending moment profile below the isolated footing is in this profile, that is below this particular point here, that is at the face of the column. The bending moment is the maximum value here, that is WL²/2, and it gets reduced to around 0 at the edge of the foundation, or in some case it may be some minimum nominal value. So this is basically the profile of the WL²/2 here. Now when we are considering the combined footing, what exactly are the bending moment profile and how do they get balanced? So this is the question that is in the mind of the new structural engineers. So basically, now instead of this isolated footing where we are considering the bending moment about only the bottom point here, now we do need to consider the bending moment for the bottom part as well as for the top part. Now only discussing about the bottom part here. Basically the things for both the foundations are same. That is, if we are considering the maximum bending moment for the combined footings also, the maximum bending moment is WL square by 2, and that shall be be there on the bottom part only. So here we can see that when we are considering the calculation of reinforcement at the bottom, we are doing nothing but WL square by 2. So this is the net bearing pressure, and this is the maximum projection. So we are doing W into L divided by 2. So in this case, for both the parts here, so when we can consider the maximum projection, either this side or this side, in the case where the footings are higher on one side and less distance on the other side, so we can simply calculate the bending moment here. And now if we talk about the top part here, so if you are good with the basics of the structure analysis, you do understand that in the case of the beams where there is a continuity, the bending moment considered is W into L square by 10. So in this case also, what we are doing here is that we are doing W into L square by 10. So 2.5 is nothing but distance between this point and this point, and we calculate the bearing pressure that is coming from the bottom. So that bearing pressure into L square divided by 10. So that is the maximum negative bending moment which is coming on the top. So if we want to draw the profile of that particular bending moment, so it shall be in some cases it might happen that it might go on the top, whereas in some cases it might happen that it might not go on the top and it might be on the bottommost point only. So that also we do need to check in the case of the combined foundations. So all these things are the basics without which you may not be a good structural designer. So always as a doctor, you should understand that a good doctor shall always understand about the body parts. Similarly, as a good structural engineer, you should understand how the bending moment and shear force may flow in your structure. So this is just a rough bending moment profile. So this is WL square by 2, and this moment is WL square by 10, and in some cases it may go on the top, and in some cases it may remain on the bottom only. And as I had discussed with you earlier also, that you may need to understand it might happen that this bending moment is higher and this bending moment is lower, maybe due to this projection being higher. So you should understand each and every part to design the structure perfectly. So we can delete this profile here. So now coming back to this point, so we can name it to CF1. Always in nomenclature there should be this difference in F1 and CF1. F1 means isolated and CF1 means combined footing, and we can enter the size here, that is 5200 by 3000. So 5200 by 3000, and depth we can enter it as 900 mm, and reinforcement on bottom can be provided 20 dia 150 mm 2 layers. So we can provide 20 dia 150 mm, and second layer can also be provided like that only. And crossbars can also be provided in the same manner. Although this should you should also understand this point here, that is the reinforcement can be different on this particular point also and this particular point also. So what you can do in this file is that, what I am trying to say here, just wait a minute. Basically the thing is that for this particular axis, it is 3000 minus 600 divided by 2, that is 1.2 meter is the projection for this particular point here, and for this particular point the projection is 1.35 minus this 0.175, so it is 1.175 meter. But as the bending moment was not the governing requirement, so that is why we are not considering both the different projections here. But in some case it might happen that this side projection may become very high and this side projection may become very lower, so the higher projection shall always govern the bottom reinforcement design. So coming back to our point here, we can just copy paste what we have written here, and similarly for the top reinforcement also we can provide 16 dia at the distance of 150 mm center to center. So I hope now the things are clear, that is how we are considering the bottom reinforcement and top reinforcement design for the combined foundation. There's also practice that you know like some people may say that you don't need to provide the complete reinforcement for the bottom part here. So for that what we can do is that we can just simply make a double layer here and just break the part here. So what basically we are doing here is that we are putting the reinforcement as per the design requirements only. We don't need to provide a all through bar here. So as the shear and this shear requirements only acts at distance of d, so we can just provide extra bars at a distance of 900 mm only. So that is what indicatively I am trying to show you here, and similarly you can terminate the bar on this particular face also. So we can extend this bar only up to 900 mm from the column face as per this one-way shear requirements. Two-way shear acts at d by 2 and one-way shear acts at d. So up to the distance of d only we have this punching shear requirements. So that is why I am suggesting you that you can do this type of detailing also. So that is also not wrong, and that shall always give you an economical design. So this type of scenario can be done, and similarly we also always shall need the binder bars also, or the reinforcement along the other axis. So I hope at the end of this lecture you are comfortable with the isolated footing design and combined footing design. If not, I shall request you to please repeat these lectures, cause I cannot explain you more than this. And if you still have any doubts, feel free to ask any questions in the question and answer sections. So I shall request you to please ask all the question answer sections, not in the message sections, so that all the people who are in this course shall have some better understanding of what exactly is the questions of the other students also. So before we discuss the detailing of the columns and beams, I want you to be thorough or be comfortable with what exactly are the provisions for the detailing of the concrete structures. By detailing of concrete structures, I mean the seismic detailing of the concrete structures. And basically, why do we need seismic detailing? Why we cannot just put reinforcement bars and expect the structure of concrete to behave elastically in the case of earthquakes? Cause it is not the nature of concrete to be an elastic. Only the reinforcement or the reinforcement in the joints that we shall provide, it can only behave as a seismic joints, and that can only be a safety factor for the structure, for the formation of hinges and releasing of energy, and the structure not to collapse. So to avoid structure to collapse in the case of seismic zones, we do need to do the seismic detailing. So you can refer IS13920 that was released in the year 2016, latest amendment. So here this is just a copy of that. So here I shall not go into deep detail, but I shall only cover it on the outside only. So there are two types of frames that has been discussed. So this is number one is a moment resisting frame and special moment resisting frame. So this is ordinary moment resisting frame and this is special SMRF. So for SMRF only we can take the response reduction factor as 5. So when we were inputting the data here in the case of this seismic definition, here we have entered the response reduction factor as 5. So if we are going for OMRF frame, that is SMRF, here you can see this. So if we are going for OMRF, ordinary RC moment resisting frame, so in that case automatically the value becomes 3. So this is the difference. And some shear walls definition is given here. So I will only care about the important things here. So the minimum grade of structural concrete shall be M20, but M25 for buildings more than 15 meter in height in seismic zone 3, 4 and 5. So although the code allows M20, but minimum shall be M25 for these particular buildings. And steel reinforcement shall be grade 415 or less, or grade FE 500 or FE 550, but with minimum elongation of 14.5%. So if you are an Indian, you should understand that the reinforcement that is allowed in the Indian scenario is not FE 500 but FE 500D. So by having a suffix D, it means that the elongation is more than 14.5%. So the beams factors are also given. That is, the beam shall have minimum width of 200 mm and longitudinal reinforcement also. That is, beam should have minimum at least 2 mm 12 diameter bars. And this diagram shows that we can use the wide beams also. Basically wide beams are nothing but for example, let us say 1 meter by 300 mm or 1 meter by 400 mm. So they can also be given in the case where more headroom is required. So coming in to this particular diagram here, this particular diagram explains the anchorage of longitudinal beam bars at exterior beam column joint. So basically at exterior joints, the top and bottom bars of beams shall be provided with anchorage length. So right now we are talking about the exterior joints, not about the interior joints. So at exterior joints, LD, that is the so it is saying that the exterior joints, top and bottom bars of the beams shall be provided with anchorage length beyond the inner face of columns. That is, this face equal to development length bar of tension, that is LD, plus 10 times diameter of bar minus the allowance for 90-degree bend here. So this acts as nothing but LD plus 10 times the diameter of this bar minus of the allowance for the 90-degree bend here. So this is also a very important detail that we do need to implement in our structure. And splicing of the longitudinal bars. So in the case where splicing are provided, the spacing shall not exceed 150 mm and the lap length shall not be less than development length of the largest longitudinal reinforcement bar in tension. So lap splices shall not be provided within a joint within a distance of 2D from the face of the column and within a quarter length of beam adjoining the location where flexural yielding may occur under the earthquake effects. So this is also important that not more than 50% of area of steel bars on either top and bottom bar shall be spliced at any one section. I want to tell you that this failure in history has occurred because of this particular point. So what they had done was that I think in around 1930 or 1940s, when there were not much data available about the behavior of concrete, what they had done was that they had provided all the splicing bars at one particular plane only. So when the bending moment was quite high, the beam simply failed. So mechanical couplers are also recognized in the construction industry, and they are always desirable as compared to this splicing provision here. So the cost of this mechanical coupler is almost same to what we do with the help of this splicing. But the only thing is that some organizations do not accept this mechanical coupler provisions. But myself as a structural engineer, I always suggest people to go with mechanical couplers only, because the cost of the mechanical coupler that is used is almost equal to the length of the reinforcement bar that is wasted into this provision of splicing. After that, welded splices shall not be used for beams for a distance equal to 2 times the depth of the member from the member face. So transverse reinforcement also. So for transverse reinforcement, this distance is very important. So according to the code, it shall be minimum 6 times diameter of bar. But according to my details that I usually give in my my work, I always tell them to provide at least 10 times the diameter of this bar. So if the dia of this tie is 8 mm, so I always request them to provide at least 80 mm of the length here. So minimum diameter of link shall be 8 mm, and these type of bars are seldom used or very rarely used. So the close spacing of links. So this is a very important point here. So in the case of the beams, the spacing of links over a length of 2D at either end of beam shall not exceed d by 4 or 8 times the diameter of smallest longitudinal bar or 100 mm. So when we are providing the beam reinforcement, so at a distance, so for example, let us say the depth of the beam is 450 mm. So at over the length of 900 mm from the column column face, the spacing of link shall not exceed d by 4. That is 450 divided by 4, approximately 112.5 mm, or 8 times the diameter of smallest longitudinal bar. Let us say we are using this 16 dia bars, so 8 into 16, 128 mm or 100 mm. So against 112.5, 128 or 100 mm, the minimum is 100 mm. So that is why in high shear zone we provide the spacing to be 100 mm only, and first link shall be at a distance not exceeding 50 mm from the joint face. So these two provisions are very much important when we are detailing the beams. After that, when we provide the columns, so the column, this provision is very important. The minimum dimension of column shall not be less than 300 mm or 20 times the diameter of the largest longitudinal reinforcement bar. So when we are using 16 dia bars in the columns, we cannot provide less the size of the column less than 16 in 20, that is 320 mm. So that is why the minimum column size that I usually preferred is 350 mm along one axis. And this is the diagram here that we were discussing here. So at the distance of this 2D from this particular face, the hoop spacing, that is these rings that we are providing here, the stirrups that we are providing here, shall not be less than d by 4. The d is the depth of the beam here, or 8 times the diameter of the smallest longitudinal bar, or 100 mm. And hoop spacing here shall not be this greater than d by 2. And here we can see that the first tie shall be at least a distance of 50 mm here. So this is basically the exterior joint, and this is the interior joint. And minimum column width shall not be greater than or equal to 300 mm, 20 times the diameter of smallest longitudinal bar. So this is basically the width that we are talking about. After that, the lap splices, the spacing of links shall not exceed 100 mm. So when we are providing lap splicing in the columns, so over that particular area, the spacing of links shall not be greater than 100 mm. So after that, the code is also guiding us that what exactly should be the lap length and what exactly is the distance of the lap splice that we shall provide. And the code discourages to, like for diameter larger than 12 mm, mechanical splicing shall always be adopted. So transverse reinforcement, the code is guiding us and about the when rectangular links are used. So all these are when you will read them, always make sure that you remember them, because without these details you shall not be be able to do the detailing correctly. So as I was discussing you earlier, so I usually go with 10 times diameter, not the 6 times diameter here. So as a designer, you have this option, because code is always recommended, not compulsion. So if you're going on the higher or conservative side, then there is no harm in that. So this is basically the provision for this transverse reinforcement for the columns, that is ties. So we cannot provide spacing not more than 1/4 of the minimum member dimension of the column. So when we are going ahead with 350 mm this column size, we cannot provide spacing more than 82 mm or 80 mm, or we can go ahead with 6 times diameter of smallest longitudinal reinforcement bar, or 100 mm. So all these points are very important when we are doing the detailing. And in this particular section here, basically what happens is that footing, this particular junction is the junction that forms the interface between all the columns and beams above, and the foundation and the earth below that. So here the code guides us that we should provide minimum special confining reinforcement in the area of 300 mm. So after that, this is the clause for the shear wall and shear strength of concrete in joint. All the calculations or all the formulas have been given here. And after that, the special shear walls provisions are also discussed here. That is, these are the minimum reinforcement requirements for squat, intermediate and slender walls. The code is also guiding us about how we can distinguish between squat, slender and intermediate shear walls. And boundary elements are nothing but the thickening of the shear walls at the ends. And after that, coupling beams, these are the coupling beams. So openings in the walls are also entered in this particular code. Construction joints, and this is basically the calculation for calculating the reinforcement requirements for the shear walls as per the IS13920. And after that, they have also entered in the gravity columns and buildings. So you should understand, take your time and please do have a thorough study of this particular code here. The code, the BIS is also providing the commentary for this particular code and some design examples for this IS13920. You can just Google them and study them. In this lecture, we shall learn how we can do the detailing of the columns as well as for the beams. So first of all, in this lecture, we shall only learn how to detail the columns. And first of all, let us say we pick this particular row here, go to view and selected objects only, and here when we double click on this particular column here, we can see this window here. I've already explained in the previous lecture what exactly all these options mean. I can repeat in this lecture. So this is basically the loader that is governing the design, that is load number 263. that is this particular load combination here. Location is the N2, PU that is axial force, and MZ and MY that is bending moment along both axes. This is the grade of concrete, grade of steel. Area of steel required is 16,1685 mm square, and percentage of area is 0.862. As per STAT, we can provide 16 number of 12 diabars. But in this scenario, we just need to see these two particular rows here. That is area of steel required and area of steel percentage. So although I only see this area of steel required only, so 116.1685. Above that we are getting 2241. So you can see that area of steel required is lesser on the bottom and more on the top. Basically what is happening here is, you can see the PU is more, that is 687, and bending moment is lesser on the for this particular column, that is 124 and 68. But 144 and 65, that is bending moment becomes higher and PU becomes lesser. And if we go up, you can see that PU becomes less and bending moment also becomes less. After that PU again becomes less, but here we can see that again abruptly the MY increases. So in this column the MY was only 59, but it abruptly increases to 225.15. So this is also most widely asked questions. So why, like some people do ask me that whether their building is showing the maximum reinforcement on the top, whether they have done some mistake in the model or not. So I must say that you have not done any mistake in the model, but only these things do happen when like at the topmost floor only, where the bending moment abruptly becomes high. So if we want to again check here, so let us say we select load case number 210 here. So when we switch on the bending Y moment here, so here we can see that the bending moment MY value is very less here, but abruptly increases at this particular joint. So we can go to labels, scale, apply immediately, and bending Y. So here we can see that it abruptly increases on the topmost point, but it does not increase for all the columns. So for this, here we can see that the area of steel required is 1145, 1641, 1850, 2338 and 2125. So this is an ideal behavior according to most of the people, but this is a non-ideal behavior. But I must say this is also ideal behavior only, and these things do happen. So you do need to detail the structures accordingly, and you as a designer, you have a freedom that you can provide lesser reinforcement on the bottom and more reinforcement on the top, cause the people who know the structure well, they know that these things do happen. But most of the newbies, or the people who are not conversant with the design forces, they might think that you have done some error in the design. So coming back to the detailing part, here we can see that on the bottom the reinforcement requirement is approximately 17 centimeters square. After that 22.41, 19, 16 and 28. So there are basically two dominating values here. Number one value is this value, that is 22.41, and number second value is 27.67. So what we can do in this case is that we can provide a maximum reinforcement, that is 22.41 from this point to this point, cause all other values are less only. So if we are providing this value 22.41, it is more than 16.85, it is lesser, and it is also lesser. So from this point to this point, we can provide the reinforcement to be 22.41 centimeters square, and for the top floor we can provide 28 centimeters square. So how exactly can you distribute this 28 value and 23 centimeters square value? So for that I have you need to remember this particular table here. So this is basically the diameter of bar that we are using, and this is the area of steel bars. So for 8 mm square, if you just simply do the basic math, that is pi d square by 4, you get the area of the bars as 50 mm square. which when divided by 100 shall gives you the area of steel bar in centimeters square. So if we are using 16 mm bars, the area of one steel bar is 2.01, and for 20 dia bar it is 3.14. So in this particular case, if we want to provide 23 centimeters square, how we can break up? So we do need to understand here that our this we do need to understand that how we can distribute the bars is also a very important concern here. So for example, let us say if we are providing a rectangle of 350 by 600 mm here, okay, and we are providing the bars here, or we can make a rectangle here of 350 by 600 mm. We can make an offset here of 40 mm. So after that we can make the edges. What I am doing here is just a rough drafting for your understanding. So we can, if we are like having 350 mm dimension here, so for 350 mm if we reduce the cover, you are left with only 270 mm. So for 270 mm you cannot provide more than 3 bars on this particular face here. So 1 bar we can provide here, and second bar we can provide here, and third bar we can provide here. We cannot provide more than 3 bars on this particular face, otherwise the concrete may face some problem in entering from this particular side, or you may, or the people who might be working on site may think that the like reinforcement is very dense for this particular column. So 1, 2 and 3 bars here, and 3 bars on this particular face, and similarly we can provide bars on this face also. So here the dimension is 600 mm. So reducing the cover, we are left with 520 mm, and 520 mm divided by this 4 gives us approximately 130 mm. So we can divide this into 4 parts. One, 2, 3 and 4. We can make it equidistant also. So 3 bars on this face and 3 bars on this face. So now we need to divide 1, 2, 3, 4, 5, 6, 12, 7, 8, 9, 10, 11, 12 bars. And the target that we are having is 22.41. So what we can do here is that we can multiply 12 into 2 to get 24 centimeters square. And how we can have 2 centimeters square? We can provide 12 16 number dia bars. So providing 12 number of 16 diameter of bars here, so we can enter the size here, that is 350 by 600 mm, and we can enter the diameter of bars also. So we can enter 12 number of 16 diameter 16 mm bars here. So providing 12 number of 16 dia bars, we can have 24 centimeters square requirement, and we can have this like this is the area of bar from foundation level to the this particular floor level here. So first floor, second floor, third floor and fourth floor level. So we can name it to up to fourth floor level, and from fourth floor to fifth floor level we can increase the reinforcement. So fourth floor to terrace we can say. So from fourth floor to terrace the reinforcement requirement was 28 centimeters here. So how we can change it from 12 16 dia bars? What we can do, we can increase the area of reinforcement requirement as per the this revised value here. So instead of 24 we need to go to 28. So that is a difference of only 4 centimeters square. So what we can do here is that we can increase the diameter of these 4 bars here. So 1, 2, 3 and 4. So these 4 bars can be 20 dia bars. And hollow bars can be 16 dia bars. So here we can enter 1, 2, 3 and 4. So we can have 4 number of 20 diameter bars, and 1, 2, 3, 4, 5, 6, 7 and 8. 8 number of 16 dia bars. So let us check whether we have met our requirements or not. So 420 diameter bars means 4 into 3.14 plus 8 into 16 dia bars. So we can sum up this plus this. So now we can have 28.65 centimeters square, and the requirement was 27.67. So this is the manner with which we can detail the columns. So similarly we can detail this particular column also. So here we can see that now for these type of situation what we can do, we can here see that approximately 25 centimeters square is requirement, then 24, 18, then it's get to 16 and 12. So what we can do for this type of scenario is we can classify type 1 for this and type 2 for this particular case. So from this point to this point, as the size of the column is same, so let us try to detail this type of column also, where the reinforcement requirement is ideally decreasing from bottom to top. So first, second and third floor level, and third to terrace. And we should not get confused between the third floor roof and third floor level. So right now we are talking about this level. So this is for second and third floor level. So here the requirement is approximately 25 centimeters square on the higher side only. So for 25 centimeters square, we have basically 12 number of bars. So how we can distribute 12 bars for 25 centimeters square? If we provide 12 number of 16 dia bars, then it shall be somewhat lesser. So it is only 24.12. So what we can do in this particular case is we can provide reinforcement on the higher side only, that is 420 dia bars plus 8 number of 16 dia bars, which gives us approximately 28.65 centimeters square. So this type of detailing can be done from up to 3rd floor level. So in this case, in this scenario, we are basically providing 28 centimeters square against maximum requirement of 24 centimeters square. And from this point to this point, the reinforcement requirement is only approximately maximum 17 centimeters square. So now we ideally need to reduce these bars here. So what we can do, we can make 420 dia bars to 416 dia bars, and remaining to also to 816 dia bars. So in this case we are providing 24 centimeters square, but right now the reinforcement requirement is too less, that is in the maximum to maximum 17 only. So the question is whether we can reduce more reinforcement requirement or not. So ideally, if I am a designer, I won't go less than like beyond this, but as a theoretical manner, what we can do here is that we can decrease the dia of let us say these two bars here. So what I'm trying to convey here, two 12 dia bars and 16 dia bars. So two 12 dia bars can be this one and this one. So with this scenario, like the reduction in reinforcement is also uniform. We have not abruptly decreased the reinforcement requirement, and we have now basically reduced it from 28 to approximately 24. So this is the maximum, according to me, the optimization that we can do in this case. Abruptly changing it to 420 plus 816 to let us say we can, some people might be thinking that why we are not just simply providing 12 number of dia bars. So in the previous lecture, we have learned how we can detail the foundation, how we can design the isolated and combined foundation, and how we can do the reinforcement detailing for the columns. Now the thing is that there are basically these two main structural elements that everyone knows. One is the beam and other is the column. Besides that, there are also shear walls etc. or footings etc. But to concentrate our focus on just on this beams and columns, the shear reinforcement for beam is called stirrup, and the shear reinforcement for columns is called ties. So in this lecture, we shall learn how we can detail the ties as per the seismic standards of the India. So if we notice, if you have copy of IS13920 2016, so in that standard basically there was this figure that was being shown here. So according to this figure, the splicing shall be done in this particular area, and the spacing of the ties for up to some distance below the and above the beam column junction here and here should be less, and here we can like increase the spacing of the ties. So special confining and reinforcement has to be provided in these areas here, and in this particular area wherever there is splicing, you need to provide the ties at maximum spacing of 100 mm. So if we will see the like the clause that deals with the special confining reinforcement here, it tells us that it should have a spacing not more than 1/4 of the minimum member dimension of the beam or column. 6 times diameter of the smallest longitudinal reinforcement bars or 100 mm link. So if we see our column here, let us say if we want to detail this particular column, so if we double click this column here, it will show us that all the longitudinal reinforcement here, but it doesn't show anything about the ties. So to see that, we need to open the stat output file here. So the beam number or the column number 674 here, we open the output file here, 674. So this is the column 674 design result here. So it says us that the tie reinforcement needs to be 8 mm dia rectangular ties at 255 mm center to center. This particular spacing is as per the IS456 or the normal concrete design. It is not as per the seismic design. So to do that, what we basically need to do here is that we need to follow these three codal requirements here. The number one codal requirement is 1/4 of the minimum member dimension of the beam or column. So the column here is of the minimum member dimension is 350 mm. So 350 divided by 4, it tells us that 87.5 mm. Second is 6 times the diameter of smallest longitudinal bar. Let us say we have used 16 mm dia bars as minimum bar, so 6 into 16, it is 96. And the third is the 100 mm link. So here we can see that, and the three values are 87.5, 96 and 100 mm. So we shall follow 87.5 mm as the spacing of the ties here. So in this particular area, as we need to go with the round number only, so we can adopt 85 mm spacing of ties here. So coming back to our file here, so let us suppose that this is the typical cross section here of the column that we need to provide here. So in this particular area from this point to this point, we can name it as zone 1, and the intermediate area we can name it as zone 2. So the zone 1 spacing needs to be 8 dia at 85 mm center to center. And if this is the the sketch or the section of the column, in that case what we basically need to do is that we also need to provide the ties here. So it shall be like this, and this length shall be minimum 10 times the diameter of bar here, that is 80 mm. And we also need to provide a tie here. So this is just a rough sketch to show you that what exactly I am trying to prove here, and we shall also provide a tie here. So this is just a single leg tie here, this one, and this is a simple rectangular stirrup. So we are providing 1, 2, 3 and 4 number of ties here. So all these ties needs to be at 8 dia at 85 mm center to center for this h/4 distance. And in the intermediate area, what we can do here is that either we can provide the spacing that is required here, although I shall not suggest you to go beyond 175 mm center to center spacing here. So for zone 2, we can provide it as 8 dia 175 mm center to center. So there is no hard and fast rule, but I shall always suggest you to restrict your spacing at not more than this minimum member dimension divided by 2. So this is just a simple thumb rule that I follow. There is no particular codal guideline for this zone 2, but for zone 1, where the code guides us that the hinge should form in that particular area, so that is why we are providing this special confining reinforcement at minimum spacing of 85 mm center to center. So this is just a like an introduction on how you can provide this confining reinforcement for a column. So in the previous lecture we have learned how we can detail the column ties. So in this lecture we shall learn how we can do the detailing of the beams and how we can detail the stirrups as per the seismic and as well as the concrete design standards. So let us say if we want to do the detailing of a beam on this floor. So what we can do here is that let us say we want to do the detailing of this particular beam here. So to make the things clear, we can select the columns also. So basically if we switch on the bending moment profile by selecting MZ, so here we can see that basically bending moment is coming on the top on the beam column junction here, and then on the midway it is coming on the bottom. So this is basically valid for all the beams here. So on all the beams here you can see that the bending moment is coming on the bottom here in the middle part, and the bending moment is coming on the top for this particular part. And if we double click here we can see that basically there are two bending moments given here. One is the positive bending moment and one is the negative bending moment, and basically the negative is this bending moment and positive is this bending moment. So you don't need to confuse anywhere. So here also you can see that basically distance is 0 and 4.5 here. So basically if we see the length of this beam here, so here we can see that starting and end there are negative bending moments, and in the middle there is positive bending moment. So let us say if we want to do the detailing of this particular beam only. So here we can see that the start is saying that we need 7 number of 12 dia bars here, and on the bottom it needs 4 number of 10 dia bars. So this is very less reinforcement according to my perception. So let us say if we want to do the detailing of this particular beam here, because the reinforcement requirements are quite high here. So the span of this beam is basically 7 meters here. So for 7 meter on the left you will see that the requirement is 6 number of 16 dia bars, and here also you can see that the requirement is coming out to be 10 number of 10 dia bars, and here we can see that the requirement is quite high, that is 3 number of 20 dia on the left portion here, that is at this particular point, and 4 number of 20 dia bars at this particular point. So basically what new people do, what they do is that they take a printout of all the beams and then mark the reinforcement on the top and bottom, like the ETABS gives us in the after the analysis. But if you are much familiar with this software, so what basically I do in the office is that I basically double click here and then directly see the reinforcement requirements here. There is no need to go to the output file to see the reinforcement requirement for this beam. If you are a beginner or if you are new to this, then definitely you need to do that. But if you are an expert, you don't need to check the reinforcement requirement for each and every beam and then do the detailing according to the requirements. So let us say if we want to detail the beam from this point to this point. So on the left, this is the starting point. On the left, the reinforcement requirement is 6 number of 16 dia bars. So what we can plan here is that we can provide 3 number of 16 dia bars all through, and the And if you want to see the area of the bars here, basically 6 number of 16 dia bars means that 6 into 2, that is approximately 12 centimeter square is requirement on the top. And if we see the bottom requirement here, so bottom requirement is only 7 number of 10 dia bars. So if we want to see the 7 into 10, basically 7 into 0.8. So on the bottom it is 5.6 centimeter square is the requirement here. And if we again go on the top here, so here on the end point, that is blue point, here we can see that the reinforcement requirement is 10 number of 10 dia bars. So 10 number of 10 dia is nothing but 7.9. And after that, if we see again the reinforcement requirement for the small beam here, so for this we can see that 3 number of 20 dia bars is requirement on the starting point, that is green point, and 4 number of 20 dia bars is the reinforcement requirement for the end point. So 3 into 3.14 and 4 into 3.14. So 3 into 3.14 means the 9.5 centimeter square approx, and 4 into 3.14 means the 12.6 centimeter square requirement. And if we see the bottom reinforcement requirement for this particular beam, you will see that 2 number of 25 dia bars, that is approximately 10 centimeter square. So these cells are the requirement for the top, and these cells are the requirements for the bottom reinforcement. So now the question is how we can detail the beams here. So what basically the thing we can do here is that we can provide 3 number of 16 dia bars all through. So if we see our cross section here, basically for every beam you need to provide all through bars, and as per the requirements you need to provide the extra bars here. As the bending moment profile is like this, so basically it starts from here and then it goes up to the bottom here, and then again it goes to the top here. So that is why there's extra reinforcement here, and that is why there's extra reinforcement for the negative moment here. Here basically there is almost a negligible requirement for the bending moment for the top reinforcement here. So we need to provide minimum all through bars here, and we need to provide maximum bars on the junctions itself. So coming back to our detailing, so let us say if we want to name this beam as B1. So for B1 we can provide minimum bars on the top itself as 3 number of 16 dia bars. So 3 number of 16 dia bars will be all through bars. So it makes 6 centimeter square all through. So basically we have already provided 6 centimeter square here, and if we subtract the all through bars with the extra reinforcement bars here, so basically the requirement now here is 6 again, and same is the thing here. So on the top left, basically here we need to provide 3 number of 16 dia bars extra here. So basically 316 plus 316, it makes 12 centimeter square here, and this is the 12 is the requirement here. On the top we can provide, basically the thing is this requirement is different and this requirement is different, but this junction is same. So basically this is the point that we are talking about. For this beam the top reinforcement requirement is lesser, but for this beam the top reinforcement requirement is more, and this all extra bar shall be same. This is the extra bar that shall go on the beam on the right. So basically we need to follow this requirement here. So what we can do here is that we can provide 2 16 dia bars extra. So by providing 2 16 dia bars here, we are providing 4 centimeter square higher than 3.5, which is the requirement. So for this beam, So to make the things clear, what I'm doing here is that I'm not making this as a table. So what we can do here is that I will do the detailing on this particular section only to make the things clear. So for this extra bar shall be as we have discussed, it shall be 3 number of 16 dia bars. The all through bars here shall be 3 number of 16 dia here, and this extra bars on the top shall be 2 number of 16 dia bars. So now we have provided 12 centimeter square here and 10 centimeter square here as per the requirement. So now we have fulfilled the top reinforcement requirement for this particular area, and on the right we can see that 6.6 centimeter square is the requirement. So to meet 6.6 centimeter square, what we can do is that we can provide 2 number of 20 dia plus 1 number of 16 dia bars. So 2 number of 20 plus 1 number of 16 dia bars. So it gives us 8.3 centimeters square. So if we go ahead with 3 number of 16 dia bars, then it shall be only 6 centimeters square, somewhat lesser than this. So this is the reinforcement requirement on the higher side only. So and here we can see, notice that as the length of this beam is very short, so this reinforcement requirement has to be common here. So instead of 2 number of 16 dia bars, we need to provide 2 number of 20 dia bars plus 1 number of 16 dia bars. So this is the way with which we can do the detailing for the top reinforcement bars. And if we switch over to the bottom reinforcement requirement here, this is the 5.6 and this is the 10. So what we can do here is that we can provide minimum all through bars as 3 number of 16 dia bars. So for this throughout bars, we need to provide 3 number of 16 dia. And extra bars, although there is no requirement here, but sometimes basically it do happens that in the case of the earthquake, the bending moment get reversed. So if the span of the beam is quite high, that is like 8 meters or 7 meters in our case, my practice is that I always provide some extra bars here, because sometimes it too happens that in the case of earthquakes, the crack develops here and the bending moment shifts around here. So that is why I am providing 2 number 12 dia bars, although as per the requirement there is no need. And here we can see that 10 centimeter square is the requirement. So what we need to do here is that we need to provide an extra bar here. So this bar shall be 2 number of 16 dia bars. So with this approach, we have provided 10 centimeter square on the bottom. So if we cross check our requirements here, we have fulfilled all these requirements here and we have fulfilled all these requirements here. So this is the method with which we can do the detailing of the beam from this point to this point. So that is a total 9.5 and with 3 columns here. So similarly, if we want to do the detailing of other beams also, let us cross check any additional specific requirements. So let us say 10 number of 10 dia bars is requirement on this point and this point, and 4 number of 10 dia bars is the reinforcement on the bottom. Same is the case here. So approximately 7 number of 12 dia bar means 7 into 1.13, that is approximately 8 centimeters square. So in this case, listen carefully. What we can do here is that we can provide 3 number of 16 dia bars all through, so it gives us 6, and we can provide 2 number of 12 dia bars extra on the top face. And for bottom, we do need minimum of 50% of the reinforcement that we are providing on the top at the bottom face also. This is a very important clause as per the Indian standards. So this is the clause that I was talking to you about, that is longitudinal steel on bottom face of a beam framing into column shall be at least half the steel on its top face at the same sections. So whatever steel we are providing here, that needs to be at least 50% of what we are providing here. Basically the thing is that always your top reinforcement requirement shall be more and your bottom reinforcement requirement shall be less for frame structure. For this gravity structure or for simply supported beams, the requirement is opposite. That is, for the bottom the reinforcement requirement is more, whereas on the top the reinforcement requirement is lesser. So this clause ensures that there is no sudden decrease on the reinforcement requirement on the top and bottom. Basically, as I also told you earlier, that in the case of earthquakes, the bending moment reversal may occur. So whatever reinforcement requirement is on the top, in the case of bending moment reversal, the reinforcement requirement comes on the bottom face also. So this clause ensures that there is at least minimum requirement for that particular scenario. So now we have studied how we can do the detailing of the beams for the flexure reinforcement. Now if we come over to the shear reinforcement, so the shear reinforcement requirement deals with this particular case, that is spacing of links over the length of 2D. That is, if the beam height is approximately 600 mm, so up to the distance of 1200 mm, we do need to provide a special confining reinforcement, and that confining reinforcement shall not exceed d by 4. That is, in our case, d is 600, so 600 by 4, 150 mm, 8 times the diameter of smallest longitudinal bar. So if our smallest longitudinal bar is 16 mm, so 8 into 16 is 128 mm, and d by 4 is 600 divided by 4 is 150 mm, and third is 100 mm. So basically it comes out to be 8 dia at 100 mm center to center only, and in the middle we can provide 8 dia at 150 mm also. So in the non-confining zone, we can provide 8 dia at 150 center to center, whereas in special confining zone area, we need to provide 800 mm spacing center to center. And if we see the stat requirements, here we can see that the reinforcement requirement is very less. That is only 8 dia at 200 mm center to center, whereas in this case it is only 8 dia at 165 mm center to center. So this 150 mm spacing is lesser than all of this. So in simple words, this spacing is most of the times governed by this particular clause only. Very rarely has happened that the reinforced shear stirrups requirement as per stat is coming more than this particular spacing. So always go for 100 mm, and if your longitudinal bar is 12 dia bars, so in that case you need to provide 95 mm center to center only, because 8 into 12 is 96 mm. So this is the method with which we can do the detailing of the beams. So in the previous lecture, we have learned how to detail the beams, columns, foundations, how to design the combined foundations. So in this lecture, we shall learn how we can design the slabs. Basically, slabs are the flexural elements that the sole purpose of the slab is to transfer the live load from itself to the beams, and then from beams to the columns, and then from columns to the foundations. So let us suppose we take this particular floor here, and here we can check the span of the slabs here, that is 4.5 by 3.5. so let us suppose if we want to design this particular slab here, so to design this particular slab here, the span is 3.5 into 4.5. Now there is a basic concept that you do need to understand before we move on to the design of the slabs. There are basically two types of slabs. One is the one-way slab and other is the two-way slab. As the name denotes, two-way slab means that the load shall be transferred to all the two directions, that is along this axis also and this axis also. So the basic convention of two-way slab is like this. So this is the system with which the loading is transferred for the two-way slab, and if we are denoting one-way slabs, then it needs to be denoted like this. So what exactly does the symbol denotes? This symbol denotes that whatever loading we are putting here, so let us say this particular loading is being acting on this particular floor here. So for that, basically the yield line, like yield line diagrams can be drawn here. Like this. So the loading on this particular beam here shall be the area of this particular area, this trapezium. The loading on this particular beam shall be the area of this triangle into the loading that is acting on it. Similarly for this beam and similarly for this beam. So two-way slab means that the loading shall be transferred in all the four directions. But in this one-way slab means that the loading is only acting along one particular direction, and this is only a passive reinforcement here. So for the relation between one-way slab and two-way slab is that this dimension, the longer dimension divided by shorter dimension, should be more than 2 for the one-way slab and less than 2 for the two-way slab. So here we can see that this dimension is too long and this dimension is too short. So this divided by this shall be greater than 2. So it is a one-way slab. That is, the loading shall be acting on this particular side and this particular side only. There shall be no loading on this side and this side. So the main reinforcement shall be along this particular direction only. But in our case, if we see the diagram here we can see that this is 3.5 divided by 4.5, and if we calculate the ratio here for the, that is longer side divided by shorter side, 4.5 divided by 3.5 is 1.28, that is less than 2. And if this dimension is, let us say, 7.5, 7.5 divided by 3.5 is 2.15. So if this dimension would have been 7.2 meters, so in that case it must be one-way slab here. And let us suppose if we check this dimension here, so this is also a two-way slab only, because 2.5 into 2 is 5, that is here it is less than 5. So here we can summarize that all the slabs that have been modeled here are two-way slabs only. So if we want to design the two-way slabs, so there is this Excel file here. So first of all we need to enter the grade of concrete. Let us say the grade of concrete is M30, Fy is 500, length of shorter span we can select it as 3.5 by 4.5 here. So it is 3.5 and it is 4.5 here. Width of the supporting beam, the width of the supporting beam is 350. So here we can enter 350. Clear cover to main reinforcement we can enter 25, and dia reinforcement steel we can assume it as 10 mm. So you must be wondering why we are entering width of supporting beam in the design of the slabs, cause it plays a very major role in designing the effective span. There are two types of span. The one is the span that we are seeing here, and if we switch on the isometric view, here we can see that the slab will only act up to from the edge of this beam to edge of this beam. So each and every standard has a particular rule set which defines what exactly is the effective span. So here also we can see that this is the formula. So in this case the effective span is 3.295 against 3.5, and here also it is 4.295 against 4.5. so this is the value which shall be considered for the design, not this particular value. And the second thing, effective D. So how we are calculating effective D? That is 175 minus 25 minus 10 divided by 2. That is 175 minus 30. That is 145 mm. So here also the discussion that we were doing previously. So in this case, the design of the slab can be done as two-way slab only. So dead load, finishing load on the slab, and here we need to consider thickness here of the slab here also. So here the span is too less, that is 4.5 into 3.5. So we can select the thickness of slab as 150 mm. And the finishing load on slab is the basically the finishing that we are applying on the top. Let us say if we are doing 50 mm finishing, so 0.05 into 24, that is 1.2 mm, 1.2 kilonewton per meter square. This calculation we had already done in the previous lectures also, and it is also applied in the form of this dead load here. So 1.2 kN per meter square. Live load on the slab can be taken as, for this particular case, can be let us say for classroom it is 3 kN per meter square. So we enter it as 3, and this is the total dead load, that is 3.75 plus 1.2 gives 4.95. This is the total live load, and this is the factor design load, that is 4.95 plus 3 into 1.5. After that we need to select the supporting condition. So here if we see the supporting condition for this particular slab here, so it is basically discontinuous on the longer side here, and whereas otherwise it is continuous in all the other three directions. So this is also a very important concept which might be an alien concept for the people who are doing the slab design for the first time. So let us brief this concept here first, that is how we can decide the supporting conditions. So here if we see that this is basically an interior span here. So if we are considering this particular slab here, this is being continuous in all the four directions, that is slab here also, there is slab here also, here also, here also, and here also. Whereas if we are considering this particular slab here, this slab has is continuous only in the three direction, that is, and it is discontinuous in the longer direction. So we need to enter one long edge discontinuous here, and accordingly it will select the AX AY values for the negative as well as for the positive moment. These values are given in the Indian standard IS456, and they're also given if you are doing design for the, let us say, American code, these values are different. So with this particular relation we can calculate the minimum AST or the bending moment and area of steel requirements, and according to the code we do need to provide minimum 0.12% of the area for the this as the minimum reinforcement. So here we can see that the bending moment requirement is less, whereas the minimum AST requirement is much more here. So as a hit and trial to make the situation somewhat complex, let us say the live load on the slab is 7.5 here. So here we can see that if we are increasing the live load here, the area of steel requirement is coming much higher. So this is just an to make the things clear to you, or to make this simple problem much complex. That is why I have increased the live load, whereas you can go ahead with 3 kN per meter square only for the classroom area. But just to teach you the other aspects also, I have increased this value to 7.5. So here we can see that area AST requirements for shorter span and for longer span, at mid span and at supports. So like this table might be somewhat confusing to the people, but you do need to target these particular cells only. So keep your eye on these particular cells here. You will see that for shorter span and for longer span. So if we draw a rectangle here, let us say this is our slab here. So in this slab, if we draw the reinforcement here, so this is the let us say we are right now we are considering only the bottom reinforcement, not the top reinforcement. So the bottom reinforcement for shorter span and for longer span, for shorter span only and for mid span and at supports. So mid span, shorter span shall be the like this maximum reinforcement at the bottom. So this is coming out to approximately 208. So if we take 8 dia at 150, then even we are providing 335 mm square per meter against 208. So we can increase it to 8 dia 175. So by providing 8 dia 175 at mid span, so bottom reinforcement can be provided as 8 dia 175, and for longer span and at mid span, that is this particular reinforcement, it can be provided only 8 dia 156. So here you can have a clear picture of the logic that I was explaining you earlier, that this is the main reinforcement and this is the secondary reinforcement. So the main reinforcement requirement is coming out to be approximately 208, and for longer span the main reinforcement is coming out to be approximately 156. So these two cells are clear to us, that is how we are considering them. So for bottom reinforcement we can take 8 dia 175 here, and let us say if we check 8 dia 200, it is coming out to be 251, that is much more than 156 here. So 8 dia 175 and 8 dia 200 can be taken for this particular slab. And after that, if we consider the reinforcement at the supports, basically at the supports we are talking about the top reinforcement. If we draw another rectangular slab panel here, this is a very important concept that you do need to understand. Most of the new people are much confused with the slab design, so I shall recommend you to read this slab design from the textbook also, because I am assuming that you must have basic knowledge of the slab design. However, I will try my best to explain you this typical concept. Once this thing is clear, the slab design is very easy. But if you are watching this concept for the first time, then you might face some difficulty. So on top face, we do not need to provide the continuous all-through reinforcement on the top. We can provide the reinforcement up to L by 3 from here. That is this particular span divided by 3. We can take it as the length of this particular reinforcement bar. So let us suppose if the length of this side is 2 meters, we can provide it as 2 meters divided by 3. That is approximately 670 mm or 675 mm. So coming back to our main topic, so at supports for shorter span, for this particular reinforcement needs to be provided as 275 mm square. So how we can provide 275 mm square? We do need to provide minimum. Let us say we provide 8 dia 125. So against 275 we are providing 402 mm square per meter. So to make the things clear, we can provide 8 dia 125 for this particular reinforcement here, and for this we do need to provide for longer span this particular reinforcement. We do need 208 mm square. So if we consider a dia 175 also, then also it is 287 mm square. So I hope the things are somewhat clear to you. If the things are not clear, I request you to please repeat this lecture. So let me explain all the things again to you. I hope you get the clear picture or difference between the one-way slab and two-way slabs. In one-way slab, this is the main reinforcement here. In two-way slabs, both the reinforcement are main, but the reinforcement along the shorter span is the main reinforcement. Now coming back to our Excel file, first of all we provided the grade of concrete, grade of steel, the spans, how we I have explained already this concept that what is the difference between the effective span and the this center to center span of the beams. And after that, width of the supporting beam, I have also explained what is the exactly the importance of this and how we do need to consider finishing load and live load. So, and this one longest discontinuous, basically there are various supporting conditions here. So according to your particular requirement, we can provide the this supporting condition, and accordingly these coefficients will vary. Now coming back to this important concept here, that is for shorter span and for longer span, for mid span and for supports, and this is the like minimum AST requirements. So here we can see that the for shorter span and for mid span and for supports, basically mid span and supports, mid span is for the this bottom reinforcement plan, and for supports is for the top reinforcement. For bottom, the main reinforcement requirement is in this particular area. For top, there is no reinforcement requirement in the central area. The only reinforcement requirement is on the edges. So what exactly is the reason why we are not providing any reinforcement in the center part of the top? Because there is no bending moment here. So as like we were discussing the bending moment for the slab, this beams here also. So like beams, the slabs also have the distribution of the bending moment. So if we are talking about the slab section, let us say this is a beam and this is a particular slab that we are talking about. If we are talking about the bending moment distribution here, it is also like this. This is a parabolic, but to make the things clear, I am just making this in the form of a straight line. So that is why the area, the like reinforcement requirement is in this particular area, and here we do need to provide reinforcement for this particular area, and again this area, and again this area. So this is basically the distribution of the bending moment profile. That is why we are, when we are talking about the mid span, we are only talking about the bottom reinforcement, because mid span only the bottom reinforcement is the requirement. Top reinforcement we do not exactly need any reinforcement here. But when we are talking about the supports requirement for shorter span and for longer span, we are talking about these particular reinforcements here, because that supports the bending moments comes on the top. So I hope things are now clear to you. And again, I am briefing this particular concept here, that is for at mid span and for shorter span, 208 and 156 mm square per meter is the requirement. Basically 208 governs because this is for the shorter span, and this is less than this because for the longer span the reinforcement requirement is lesser because this is a secondary reinforcement. And if we are talking about supports, the supports reinforcement is much larger than the bottom reinforcement. Basically, let me explain this concept to you also, because this is a very important concept. 100% cases, it do happens that this bending moment value is much larger than this bending moment value. So for top reinforcement, the area of steel requirement will be much larger as compared to the area of steel requirement for the bottom span. So if you will see a drawing in the future which showcases that the top reinforcement for slab is larger than the bottom reinforcement, then that drawing is correct. You don't need to worry about that. So here also you can see that for supports the area of steel requirement is very much larger as compared to this. For supports it is 275 mm square, and but for mid span it is only 208 mm square. So if we are talking about a top reinforcement here, we do need to provide 275 mm square per meter here, and for this particular reinforcement we do need to provide 208 mm square per meter. So you like do practice some other slab designs also. If you are facing any problem, then you can ask me in the question and answer sections only. Please don't put any questions in the message sections, because I want that all the people should know what exactly are the questions of the other students. So I hope things are now clear to you. And after that, there is also another important concept, that is we do need to control the deflection of the slab also. So that is a very important concept that you do need to understand. And this concept is also applicable for the American standards and Euro standards also. But this graph that we are working here is for the Indian standards. So percentage of tension reinforcement, basically the reinforcement that we are providing here. So tension reinforcement is the one that we are providing in the form of this particular reinforcement, that is for the shorter span and for the bottom reinforcement. So if we provide this reinforcement as 8 dia 150 mm, so we are providing 335 mm square, so percentage of tension reinforcement is 0.28, and this fs value, that is 0.58 fi AST required upon AST provided, is approximately 180. So we do need to understand this graph here also, that is percentage tension reinforcement. This value can be seen from the x-axis and 180 can be seen from this graph here. Accordingly, we do need to calculate the modification factor. So 0.28 lies around here, and 180 lies around here. So modification factor comes out to be approximately 1.6. So if we enter the modification factor as 1.6, the effective depth required is 79 mm, which is much less than the D that is already provided here. So the deflection check is okay for us. So I am for your easy reference, this graph or this shapes I am just leaving it here just so that you can easily understand. If you do not need this, you can just delete these from your Excel file. So I hope the things are now clear to you, and if you are not able to understand the slab design, just read a textbook and then listen to this lecture again. I hope the things are now clear to you.